Okay. Um, Hello, everyone. Uh, this is Hao Su from UC San Diego, and I'm going to host the afternoon session according to the ICCV schedule. Okay. And I hope that you loved the talks this morning, and we will have more exciting talks in the afternoon. And also, after all the talks are finished, we will have a panel discussion where our host and the speakers will together to discuss the future of this field and some of the hot topics that is worth further study. So for the next, we're going to have Professor Hod Lipson to give us a talk. Let me briefly introduce Hod to you. Professor Hod Lipson is working in Columbia University in the areas of robotics and artificial intelligence. He and his students love designing and building robots that do what you'd least expect robots to do: self-replicate, self-reflect, ask questions, and even be creative. Hod's research asks questions such as, can robots ultimately design and make other robots? Can machines be curious and creative? Will robots ever be truly self-aware? The answers to these questions can help illuminate life's long, big mysteries. As an award-winning researcher, teacher, and communicator, Lipson enjoys sharing the beauty of robotics through his books, essays, and public lectures, and radio and television appearances. Okay. Hod is directing the Creative Machines Lab, which pioneers new ways to make machines that create and machines that are created. Okay, that's the introduction, and let's welcome Hod to give us this talk.
All right, thank you. It's a pleasure to be here. I hope you can hear me.
Yeah.
Okay, wonderful. I'm going to talk a little bit about this question that you just mentioned as one of my research foci, and that is this question of self-awareness. Can machines be self-aware? Can they sort of do we even know what self-awareness is in humans, and so on? So it's a really long quest. I would say it's sort of my career goal is to sort of make a dent in this very deep philosophical questions of, can things that are not human be self-aware, and what does it mean, and where is it actually going? And I'll start with sort of my very shallow but I think common observation is that we humans have this incredible ability to imagine ourselves in the future, and we can imagine ourselves long term, and we can imagine ourselves in the immediate future, and we can use that imagination to plan, to contemplate, to make decisions. Do I do this? Do I do that? For example, if you're all looking at this tree here, and you can, and I ask you, how would you climb this tree if you were right there standing in front of it? You can imagine yourself. You can almost feel yourself grabbing this branch or that branch, or putting your leg here and there. You can see yourself climbing that tree. You can imagine what you would do, and then if you had to actually climb this tree, you would probably be pretty good at it in the first time, just because you have this ability to simulate yourself. Now, so we humans, we can simulate ourselves into the future. And how do we do that? Now we know that humans probably learn this ability to simulate themselves, if you like, into the future. We learned it when we were babies. We play around, we move initially randomly from the cues and feedback that we receive. We gradually build what I call a self-model, a self-image, if you like, a notion of our geometric self, where we move and how we move, and how do muscles connect to kinematics and dynamics and so on. And arguably, this is a very simple, crude model, maybe similar to a forward kinematics model. But the reality is that all of our notions of self-awareness is perhaps extrapolations of this kind of model to other things, where we will go, how we interact, what will happen in the long term, in the short term. So robots, typically every robot today has a simulator attached to it, but typically that simulator is designed by a human. there's a human engineer sitting and assembling a simulation, and a lot of the teaching of robots is happening in that simulation. If you look at humans, nobody designs a human simulator and teaches us thing in it. In fact, we learn our own simulation from scratch as babies. So the question I want to talk about today is, how do we actually learn that self-simulation from scratch, and how does that happen? Does it happen, and can robots do it the same way? Now, to put this in context of reinforcement learning or model-based reinforcement learning, there's a lot of work on reinforcement learning that uses data to create a model. But what I want to emphasize here is that we're taking that general model that's typically used for reinforcement learning and breaking it down to sort of a convolution of two separate models, a model of the world and a model of the self. Now, why would we want to break down that reinforcement learning model into two submodels? Because the model of the world is changing. This task specific, it changes with time, depending on the horizon and so on. But the model of self is constant. It's task agnostic. It repeats. So in other words, if you're walking down the street, you can use that same self model that you used to walk down the street to actually go ahead and climb a tree. It's the same self model that can be used across different tasks. And this is why it's so profoundly useful from an evolutionary point of view to have a self model. It allows you to carry tasks, to revisit tasks in the past, and to carry actions into the future. Now, this is one step in a hierarchy. My guess is that there's a whole lot of hierarchy underneath this. Even the world, the self model of the world, the model of the world can be broken down into different parts, and the model of the self can be broken down into separate parts. Model of the hand, model of the torso, model appropriate for walking, a model appropriate for driving. So our self model also has this hierarchy. But for now, let's focus on that top model. So this idea of self-generated self models can be used to do lots of different things. So here's an example of an application of this self model to a robotic arm. You can see in the beginning, you can see the shadow. The self model has nothing to do with reality, completely wrong. But after about a day of training, the self model, which is being drawn in the shadow there, doesn't match the real robot perfectly, but it is close enough that for this particular task can be completed with 100% accuracy with this very crude self model. Here's another example. We took this robot and we broke it. We replaced one of its parts with this crooked orange or red part that you see on the screen. The robot can very quickly realize that its predictions don't match reality. It can collect more data, adapt its model, and then use that new self model to continue with the task as if nothing had happened. And that additional data to create the self model is very minimal. So the question is, how does this transfer to other robots? Can this idea, the idea is very general. It should be applicable to any kind of robot, any kind of task, any kind of situation. And that's kind of the thing we're working now in our lab, is to try to expand the way that this self model is learned, its richness, find out what kind of data it needs. Do we want ensemble of models? Can we use active learning to learn more quickly? Can we transfer between similar robots? There's a lot of interesting questions on how these self models evolve over time. And of course, there's a question of what is the architecture of the self model. And we're exploring lots of different ideas around these self models, from recurrent networks and networks that feed into each other to a cascade of networks like you see here. We want to look at transformers and other type of architectures that could be used to learn these self models in a way, again, that's transferable between different tasks. And all of these models, what's common to them is that they take actions, again, and predict states, but they do that not necessarily immediate states, future states, long-term, short-term, lots of different applications. So let me show you a little bit of some results and what's the advantage of having this kind of self-model. Because again, you might be asking, I can just use reinforcement learning, what's the big difference? And it all boils down to data. So let me show you how this works. So let's take this simulated robot to begin with. It's the famous ant. It has 4 degrees of freedom. first it collects data. This is the baby in the crib, just moving around randomly, collecting data. And the data here is tuples of actions and sensations, maybe motor commands and accelerations or something like that. So a lot of actions and sensation. That huge database is then used to create a self model. And that self model, if you like, is a simulation of the robot that can be used to train the robot to do whatever we want. For example, to move forward. Now, if you took reinforcement learning and you gave it access to 100,000 samples, this is the number of samples used to create the self model, it cannot do very much. At the bottom there, you're seeing a movie. Now, yes, I know it looks like a static image, but it's really a movie of a robot that is not moving almost at all. It's moving a little bit, because that's all the reinforcement learning could do with 100,000 samples. You see, reinforcement learning is very, very hungry when it comes to data, and you need to train it from scratch almost for every different task you're doing. This is what evolution cannot afford. We cannot afford to learn how we move and how we operate from scratch every time we do a new task. This is why you need to be able to transfer across wildly different tasks. And we can only do that if all these tasks have a common thing. And the most common thing about different tasks that we do is us, is that we do it. And therefore that self-model makes sense as the common thing to not to relearn. Now, if you take that self-model again, it's sort of comparable to what reinforcement learning can do with 10 times more data. So reinforcement learning can get there, but it just needs more and more data because it doesn't have the access to that self-model. So in fact, if you compare reinforcement learning, which is the red curve, it gets better and better with more data. In fact, it can do better than what a self-model can do. So you can see on the right, you can see the gap. When you have a lot of data, reinforcement learning does really, really well, better than a self-model. But if you're constrained in the amount of data that you have, and constraints in data are only happening in the real world. In simulation, you can simulate for eternity and you can collect as many data as you want. You can run simulations on Google and whatnot and get 200 years worth of data. But with a real robot in real life, you cannot collect a lot of data. So when you have only 100,000 samples, you can see there's a huge gap between reinforcement learning and reinforcement learning based on a self-model. Now that gap is for an 8 degree of freedom robot, but the question is, how does that gap or the ratio between self-model and without self-model change with the number of degrees of freedom? So here's the classic 5 robotic systems in simulation with different degrees of freedom. The hopper has 3, the ant has 8, the walker has 6, and the humanoid has 16, and so on. There's a lot of these, and you can see how they do with 100,000 data points. So here's the random babbling to collect data to create the self-model, and here's how the performance is with 100,000 samples. And here's what reinforcement learning can do with the same amount of sampling in the real in simulation. So you can see it's not doing very well. In fact, it needs 1 million samples, again, tenfold, to get even close to what a self-model can do. So in fact, if you take, so you can see that gap for 3 degrees of freedom is fairly small, meaning a bacteria with 3 degrees of freedom doesn't need to have self-awareness. But a humanoid with 16 degrees of freedom has a huge gap between what a self-model can do and what reinforcement learning can do without a self-model. And in fact, we hypothesize that that gap increases the more degrees of freedom the machine has. In fact, that's our driving hypothesis about why humans have self-awareness and maybe ants don't. It has to do with the number of degrees of freedom. It has to do with the number of tasks and so on. Is it worthwhile to collect that data to create this self-model to begin with? In fact, in some rudimentary experiments that we've done, which we are now repeating again in reality, it turns out that the more degrees of freedom you have, the greater the gain you get by having a self-model. And the factor of gain is on the left. And again, this is not percentage. This is the actual factor of gain. You can get 100-fold performance gain with a 6 degree of freedom robot. You can get a 500-degree performance gain with a robot with 16 degrees of freedom. And I believe that with something like a human that has, I don't know how many thousands of degrees of freedom, the performance gain is incalculably beneficial. So here's an example of flying this on the real world. This is a robot. This is a very simple robot, again, babbling to collect some data. And here it is walking in reality based on that data alone. Now, this is not a particularly interesting way of moving forward. And I hope that we'll be able to report soon a more elegant way of moving forward. But it is moving forward nonetheless in a way that it would be hard to find in reality. Let's move and see some more. An example of the same robot learning to stand up. Again, all it was rewarded is for its ability to stand up, to increase its Z height with the same model. So you see a different task, but the same model can be used, self-model can be used for that task. Okay. So we're trying out lots of different things. We're trying out ways to make that self-model be able to have deep look ahead. We're looking at ways to have that model, self-model, be created using data that's collected with active learning. Lots of different open questions. We find that the ability of the self-model to be used dynamically to do long-term look ahead greatly amplifies the value of the self-model. I won't go into details of that, but we're also applying it to lots of different systems. Here's one of our favorite robots in our lab. This is in simulation where we're trying this first. It's a soft robot. And soft robots are hard to teach. They have many more degrees of freedom. The degrees of freedom are very difficult to simulate. They're very difficult to control. And so I believe that when it comes to soft robotics, self-models are going to be the only way forward, because it's sort of almost hopeless to try to simulate these kind of things accurately. So you really want to collect a lot of data in reality and use that to create a self-model. We've also been using this for robots, not just to model themselves, but to model other robots. And this is a very interesting line of research. It touches on this very interesting area called theory of mind. Can machines understand what other machines are doing and how they work? Can a robot look with a camera at another robot and understand how that robot works and see, oh, that other robot has wheels, it cannot jump over the fence? This is again, we humans are terrific at doing that kind of thing. My dog knows immediately what other animals can and can't do when they're being chased. So it's, again, from an evolutionary point of view, understanding what other agents can and cannot do and what they're planning to do has a huge advantage. And we're seeing that robots can do the same thing. And behind the scenes, this is exactly the same architecture of a self-model, except that self-model is applied to another robot here. These are snapshots from a recent paper we've published on robot hide and seek. These are physical robots that play in the playpen. And the ability of one robot to hide depends on its ability to predict what the other robot can see and how it can move and where its camera is and all that. And all that is completely trained spontaneously, and it's very interesting. It's the same idea of self-modeling. Here's another example, another research project that we're doing in our lab. This is our humanoid face. It's a soft robotic face. Because it's soft, you can see its face can change, its lips can move, it can make gestures and so on. And this robot learns to imitate a human, very much like a baby can smile when you smile back at it. And to a large degree, it's done that because it's looked at its camera for a long time, and it was able to create a self-model that relates the relationship between motion of its sensors and motions of its skin. And once it has that self-model, it's pretty easy and straightforward to make it emulate a human, because it can see itself in the future. It can see what its face is going to look like when it pulls this muscle or that. So again, the same application of the same idea of self-modeling applied to facial imitation, if you like. So lots and lots of application. I think this is going to be key because, again, soft robotics like faces are very, very difficult to emulate and to simulate. So one of the things we're working on now is to see also how much this is transferable between different robots. So we're building a series of these modular robots, and the question is, if you have a self model that's developed for robot A and a self model developed for robot B, can you somehow combine these two robots, A and B, these self models, to create a new self model that is can sort of interpolate that to create a new self model that gives you a head start for robot C, even if it has a slightly different configuration. So lots of exciting ideas, lots of opportunities for new architectures, for new learning paradigms. Again, we're not necessarily developing new machine learning techniques, but we're looking how to apply all these fascinating techniques to improving the ability of machines to model themselves. Thank you.
Excuse me, maybe I have a question. I didn't really get what a self-model is, although I see it's super powerful. Is it a model-based reinforcement learning or similar kind of ideas? Maybe like
Yes, it's a model-based reinforcement learning, but the self model itself, that model is separated to a model of self and other models of the task, models of the environment. So in traditional reinforcement learning, you have a model that sort of encompasses everything, the task, the robot, the world, it's all jumbled in one thing. And I think that this is very, very inefficient, because when you have a robot in the real world, you're doing different tasks, but with the same body or with the same hand. And the question is, can you do all these different tasks and separate out a model of the self from the model of the rest of the things?
I see. So could I understand, like, for example, here we're in ICC, we're in ICCV, and there'll be certain listeners who are interested in the role of computer vision in your like agenda of self-modeling. Does it mean that we use vision technique, for example, segmentation, to separate an observation of like I don't know, some of the
Yes,
external states relevant to yourself from the rest?
exactly. I think that's a good angle. You know, we haven't done that, but the ability to separate the environment from the self is essential to create a self model, because you need to know, oh, that tree that's moving over there, that's not part of me. I don't need to model that. So how do you separate the self from the environment? You know, yeah, you can think of this as segmentation, visual segmentation, and we have done work which I didn't cover here on visual self models, which is a very interesting thing where you sort of can see what you're going to look like without necessarily understanding the kinematics, but you can generate the visuals of that. And then it's literally visual segmentation. But I would say if you actually, it's a good way of thinking about it. It's sort of almost dynamic segmentation, where you separate the dynamics of the world from the dynamics of the self. So that segmentation is key. Absolutely.
Okay. Okay. I think we still have 7 minutes, right? Will we have questions from?
Can you hear me?
Yes.
Yes. Very nice talk. Very interesting. Very
Thank you.
nice work. So, quick question for you. Once you have this model, so I have two questions. When you have this model is not a physical model. It's basically kind of like a neural net representation of whatever agent you care about. And then what do you do with it? Do you do some sort of like model-based control, or how do you use these to project into the future? Are you doing somehow running the dynamics on it, or
So, exactly. Yeah. So let me answer that first question. I can never remember two questions at the same time. So, so yes, that self model is in our case a dynamic model, which inputs, let's say, the angles or the torques going into the motors, and it outputs, let's say, the accelerations of the center of mass of the robot. That would be an example of a very simple dynamic or simple dynamic self model. But you can have more complex self models that, for example, input the visual scene and the motor commands and output what the next visual scene is going to be. So what is the robot going to see next, given this is what it's seeing now, and here are the motor commands, that the torques that are going into the motors. That's an example also of a self-model. So, I'm trying to really say here that there's many varieties of self-models, and they're suitable for different tasks. But the key thing is that no matter what task you do, that self-model is probably transferable between different tasks. And there's 1,000 different ways to create that self-model. We use the dynamics as you described. Think of it as a simulation, a simulator that you can plot it. Now, in the old days, meaning 10 years ago, we gave it the physics. We said, okay, you have to obey Newtonian physics, but now, so that was a shortcut because there was no deep learning and all that 10 years ago. So we had to do a lot of shortcuts. Today, the self-model is completely, it's end-to-end black box. It just takes in the torques, the motor commands, and outputs the accelerations. So that was your first question. I don't know if that answers it.
Right.
And you had another one.
Yes, it does. It does. And let me just, well, we have time, so I'll keep asking. So now I think that if you have like a data-driven model, like some sort of neural net, then I take it that it's easy to take, for instance, partial derivative, so that you have some sort of like model-based control. You use the tool, the black box, and it provides everything that you need to do what you need to do.
Exactly. Right? Exactly. You can do all the classic control theory on it. You can do error margins. You can test it. You can see how far you can go. Yes, exactly. Yeah.
Okay. So now the second question. The second question is, I don't know if I got it right. You said something, and I want to make sure that I understood what you said. You said that we're not looking at simulation, we're looking at just data from reality to help the self-model basically come up with the right policy, let's say, to make the robot move the way the robot is expected to move. So you don't want to use the data from simulation because it's not reliable, and this like sim to reality gap is an issue, or why don't you use it? Or did I get it right? Or maybe
okay. So I'm not sure when I said that, but I do agree if I did say that, in that ideally we want to throw this software on a real robot and not have to bother with the simulation at all. And why? I mean, this is largely because we don't want to spend time building a simulation. And I think that, I mean, this is more of a, if a simulation is very good, then yes, I agree with you. You can take the simulation, you can bootstrap the model in simulation, and then take it down to reality later on. But if simulation is not very good, then you actually can create a sort of local minimum that's very difficult to climb out of. So again, in my experience, it's almost a religious thing. I want to do everything on the physical robot. But yeah, if your simulation is good enough, then you can pre-train it in simulation, and then do the last steps in reality.
Right. So you would take the model, the self-model, so you would have in that case to have also like a Newtonian model of the self-model.
Yeah.
And based on that, you pass the data to the self-model, which does something with it, and
improves it. Okay, but this is a subtle thing that you have to be working with physical robots a lot to appreciate. I've done this a lot. I've tried this a lot, and it turns out that, for example, the self-model, you can make small mistakes in simulation that cause robots to not transfer into reality in a big way. For example, one of the biggest things, the biggest reality gap, causes for reality gap is lag time in actuators and in sensor. Lag time. You see a camera, by the time the image goes in, process, you get, you lose 100 milliseconds between you send a command to the motor, the magnets need to energize, you lose 200 milliseconds. That throws off the policy completely. So if a simulator can simulate these things, great. If the simulator does not account for lag time, it's going to be creating a very, very bad starting point for the self-model. And so we've learned this in blood. And so we are very skeptical about simulators, but yeah, if it works, it's always a good way, exactly like you described.
Okay, good. Well, thanks so much for answering my question. As I said, Great stuff. Really
Thank you.
enjoyed the presentation.
Thank you.
Thank you very much. Thank you for the great talk. So I think it's time for us to listen to the next speaker, Lerrel Pinto. Well, actually, Hod, we're going to have a panel discussion. Yeah, if you feel interest to discuss about like a simulator versus non-simulator, you can. Well, you're extremely welcome to join. Yeah. Okay. Yeah. Okay. So let me continue to introduce Lerrel. So Lerrel Pinto is an assistant professor at NYU, and he is affiliated with the Center for Data Science. And he's previously a postdoc fellow at UC Berkeley and received his PhD in robotics from CMU in 2019. In his research interests focus on machine learning and computer vision for robotics. And today, Lerrel is going to introduce the topic, bringing self-supervision from simulation to real robots.
All right. Yeah, thank you for the introduction. All right, so let's get started. Let me just see if my, All right, so what I'm really interested in is to bring robots into the real world, is to bring the sort of physical hardware into the world that we all live in, right? So this is a video over here from Ari Kando's Netflix show, and what I think it really highlights is the large amount of visual diversity and the unstructuredness of the world that we live in, right? Now, of course, if I take our state-of-the-art robots and throw them in these environments, it's probably not going to do anything. It's probably not going to solve any of the tasks that we as humans want them to solve. So let's first go over what are the key challenges over here in trying to get these robots to learn in these environments. So I think the first challenge, and probably most relevant to the ICCV audiences, we need to really deal with image-based observations. So let's say you're a self-driving vehicle and you see a scene like this and you need to reason about what to do over here. Doing this from images is hard, but if you know what the underlying state is, let's say where every pedestrian or every vehicle is, it becomes a lot easier because the amount of free space and the dimension of the problem is much smaller, right? So if a dimension is much smaller, we can sort of intuit that it should be easier to solve these type of problems. But how do we get the state information in the real world, right? If you have a self-driving vehicle, you need to put this large suite of sensors on the car, which is expensive. Or if you're doing manipulation, you need to, again, have this customized rig on top of your scenes in order to obtain the state information. Now, if you want to bring a robot into your home, it's hard to do either of this. It cannot be too expensive. You also really don't want to have these large rigs inside your home. Then I think there are multiple environments in which the notion of state itself is either ill-defined or way too high-dimensional. For example, if I show you a piece of cloth or a knotted rope, what is the state of that cloth or rope? Or if I show you an image of a tree, what is the state of the tree, right? So in all of these cases, obtaining the true underlying state of the world itself might be a very hard problem. So then the second issue we have in robot learning is that we want our robots to reason over long horizons. So what does this mean? So let's say, again, we have this example of the self-driving vehicle over here. It's easy to say what happens in one step. Let's say I ask a one-step question of what is in this image. For this, we already have really good models for it. If I go online, I find some online models. I can easily input this image and I get really good outputs that there's an adult, there's a person, and there are cars and streets in this image. But if I have to ask the question, what should I do? Like, where should I go in this image? Should I go straight, left, or right? This is a much harder question to answer, because answering this question means that you have to understand and reason about where all the people are going, where all the cars are going, where are the lanes, etc., etc. importantly, what it means is that every time you make an action, right? Every time you input an observation X and output an action Y, that action, it affects what you see next. And this issue of like having a sequence of decisions, it makes this problem hard to learn. Now, of course, if you're able to recast this problem as a one-step sequence, it becomes a contextual banded problem, for which we have good methods to solve. In some of our past work, we have shown that you can use these ideas to figure out how to grasp objects, fly drones, and even use these low-cost robots in people's homes. So if you can recast this problem into a one-step sequence, it's, you should try doing that. But the issue with this is that it's hard to recast a general robotics problem into a one-step sequence. And so in this talk, I'll go over a few ideas which can solve both the visual learning aspect and also the aspect of trying to reason over long horizons. Now, the general recipe we'll be using over here, it consists of 3 steps. The first one is we're going to collect visual data. So this can either be in a simulation or in a real robot, or you can train first in the simulation and then evaluate on a real robot. But this is sort of like the first step for any learning problem, where we have to start with collecting the data. Now, once we have the data, we are then going to learn visual representations. And again, over here, you can use quite simple neural networks, or you can use really complicated ones as well. But the sort of high level over here is that once you have this data, we're going to learn some low dimensional encoding or a representation of those visual observations. And then finally, once we have a visual, like a low dimensional feature or representation, we are then going to optimize the behavior on top of those representations. Now, to optimize this, we can either use like model-free policy learning, we can use MPC, imitation learning, or any optimizer of your choice. Okay, so now let's see this recipe in action in a few cases. The first one I want to go over is model-free RL. So as most of you might already know, but just to give a quick recap, in RL, we have an agent. This can be a robot. It applies actions into an environment. So the environment is the world that you're in. And then once it applies actions in the environment, it returns observations and a reward. Now, the goal of any RL algorithm is to maximize these rewards. In terms of the observations, you can either have image observations, which is high dimensional, as you can see over here on the top, or you can have a low dimensional observation, which can be the underlying state. So that's a state observation. And as I've sort of mentioned earlier, if you learn on image-based observations, because it's high dimensional, it probably is going to learn much slower than if you learn on this true underlying state, which is low dimensional over here. So to sort of like just see in terms of numbers how slow this is, here is an experiment, I think from 2018. So this is on the simulated Mujoko environments. You can see like a picture of the image in the Mujoko environments in the bottom right of the graphs. In blue line, it is what happens if you train with states. And in green line, it's what happens if you train with the images. And clearly, as you can see that if you train with states, it learns much faster than if you train with images. In fact, it's around like 1 to 2 orders of magnitude faster to train with states than to train with an image. And so the sort of like inspiration from this is that if you can somehow obtain a low dimensional state or something like a state, if you train on that state, you should hopefully learn a lot faster than if you're training on the raw images. Okay, so this notion of trying to learn this low dimensional feature from the image is representation learning. And in the context of model-free RL, what this means is that you have an observation, which is high dimensional. It goes through an encoder, and the output of the encoder is low dimensional. And then once you have this low dimensional feature or the representation of the image, you feed it into the RL optimizer. right? So this RL optimizer can be any of your favorite RL optimizers that operates on something low dimensional. Now, a tricky question over here is, how do you actually train this encoder, right? Because the only loss signal for RL is through the RL optimizer over here. And as we know, that this RL signal, it may not be as good, right? So the first reason why this is hard to do is because if the RL signal is too weak by itself, the encoder will not learn that well. And so what this means is that you need to have some auxiliary training procedure to train this encoder. Now, pre-2018, the standard way of doing it was either through something like an auxiliary task or an autoencoder, but it gives a gain, but it's still not enough to go from state-based RL to all the way, to go from image-based RL all the way to state-based RL. Okay, so how do we solve this problem? Now, what we have seen post 2018, at least in computer vision and NLP, is self-supervision, right? We have all of these methods which do self-supervision, and it shows that you can learn a good representation without like any explicit like labels or supervision. And one of the key interesting ideas which transfers well is the idea of using augmented data. There are several works over here. I've listed a few of them. And in RL, we do exactly the same thing now. So we take our standard RL procedure, but we just add an augmentation right at the input. So let's say you have an observation on the left. You can see it's called an XT. You apply an augmentation, which can either be a color jitter or a cropping or any of the standard augmentations, and you just feed those augmented views as input into the RL procedure. It's quite straightforward. So if you have any RL algorithm, this is just like a plug and play thing in the input. And this actually works quite well. So if you look at the results of this work in gray line, so let's look at the top left. In gray line, it is state-based RL. So that's the one which usually trains a lot faster. And in the blue line, it's what happens if you just simply do this augmented data during training. And in most cases, just doing this augmented training, at least on the simulated Ujoko problems, it gives you significant amount of gains. Of course, there are some cases where it's not as good. For example, in the middle, you can see a few examples where state-based RL is still a lot faster. And this is usually because it's a more sparser reward environment, and it takes more time for image-based learning to work with the sparser rewards. Okay, so more recently, what we have done is we have tried to sort of add in more of the ideas in augmentation, make it faster to train. And now what we're able to do is we're actually able to train image-based policies on all tasks in the DM control suite. So even on things like the humanoid, we can train a visual RL policy. So an RL policy which takes just this raw image as input. Now the code for all of this is also public. So if you're interested, feel free to download it and try it out for yourself. Okay, so the general recipe over here is that we are collecting visual data inside a simulation. We learn a representation through the augmentations, and then are optimizing the behavior through free RL. And of course, since it's a whole like end-to-end learning scheme, all of these things are happening in a loop of some sort, right? So it seems like there's like a catch over here, right? Because we're using the RL signal to train the encoders again. We're still using augmentations, but again, the main driving force of the learning is through the rewards of the RL process. So the catch over here is that learning a good representation, it still requires a reward signal for the task. And so this means that if I change the task, I need to again retrain all my representations from scratch, right? And what this normally means is that these representations, they don't transfer from one task onto another task. So how do you fix this problem? We just try to remove this part of the loop, this red arrow over here. So instead of training it on a task, what we do is we train it on an exploration problem. So we use unsupervised exploration to learn the representations. And then once we have learned these representations, we can then just do model-free RL on top of those representations. Just treat those representations as the state and just do model-free RL on that. And this works fairly well as well. Okay, so the key takeaways from this section is that if you use ideas in self-supervision, mainly augmentations in the data, you can get a significant improvements in the performance of these visual RL agents. And what we're seeing more recently is that image-based RL is closely approaching the performance of state-based RL. It's not there yet, but it's closely approaching it. All right, so this is a embodied AI workshop, and I'm sure a lot of you may be thinking, where's the robot, right? Like we want to see a real robot. So with that in mind, let's go into the next section of the talk. So over here, what we are looking to do is we are looking to make objects, or we're looking to manipulate objects from an initial state into an a priori unknown goal state. And to make things more challenging, let's work with an object which is a deformable object. Let's say a rope over here, right? So you have a rope and you want this robot to manipulate this rope such that it reaches any goal that you ask it to reach. So how can you go about solving a task of this sort? So if you look at the SAP from model-free RL, we have this loops everywhere, right? So we have to collect data, learn representations, optimize, and there are loops in this whole process. And the problem with loops, at least in robotics, is that it means that you have to collect more interactive data on the robot, which is not ideal. So instead, what we're going to do is we're going to remove all the loops and do each thing one by one without an arrow going backwards. So we're first going to collect random interactions inside a simulator. We're then going to learn a representation on that data. These representations are going to be it's going to be a predictive one. So it'll be able to tell you what's going to happen next. And then since these representations are predictive, we can then use those representations and plan with them to optimize behavior. All right, so all of this, it sounds very high level. So let's look at exactly how this is trained. So first, to collect data, we use a Mojoko simulator where we have a rope and we apply all these random actions on this rope. So let's say at some time step T, you have an image rendering over here. You apply an action which is shown in the red arrow, and the rope moves from IT to IT plus 1. And we know what action was applied because this is a simulator. Now, I'm also going to call something ineg, which is a random sample from the data set. Okay, then what I'm going to do is I'm going to create an architecture which we call a contrastive forward model. So what's happening over here is we are first going to use a feature encoder, G theta, to encode all of these images, right? So we have a ZT, which is the encoding of IT. We have a ZT positive, which is an encoding for IT plus 1, and a Z neg, which is the encoding of the negative example, which is just an arbitrary example from a data set. Now, we could do just a standard contrastive loss on like using ZT Z pos as the positive pair and the Z neg as the negative one. But over here, since we want to learn a predictive representation, what we do is we also embed a predictive model inside this contrastive loss in some sense. So we have a predictive model F phi here, which takes as input the ZT, it takes as input AT, and it outputs Z hat T plus 1, which is supposed to be the encoding of the next time step, right? And now we apply the contrastive loss with Z hat and Z positive as the positive pair and z hat and z neg as the negative pair, right? So it will try to pull the positive ones close to each other and pull apart the negative examples so that they are far away in the representation space. Now to train this, we just use the standard info and CE loss. The only difference from standard contrastor models and this work is that the similarity function that we use is not the cosine one. It's the exponential of the negative mean square error, and it's because there's like certain properties of a predictive model which make this similarity function more easier to work with. Okay, so once we have trained this, and let's say you want to now make or manipulate an object from a start state to a goal state, what you do is you take the image of the start state, you encode it, let's call that ZT. You take the goal state, you encode it, that is ZG. And now you search for actions such that the prediction of what happens next is close to ZG, right? So you're just doing one step MPC where you're saying, what's the best action I can take right now that will move my representations from start state to goal state, right? And you find an action, you apply that action, and you keep doing this again and again. So you keep planning at every time step until you reach a state where the ZT is close enough to ZG. Now, the nice thing about having a model over here is you can use the same model to go from any start state to any goal state. So in this case, we use the same model trained on ropes to go from a different start state to a different goal state, as you can see here. So this also works not just on ropes, it works on cloth. Of course, so over here we have to learn a different model since it's a different object. But now again, you can sort of start from an arbitrary start state and apply and do this one-step MPC to go to a goal state. So in this case, the goal state is the cloth being spread out. Okay, let's see this in terms of a video. So here is the rope. The goal state is shown on the right side. And I think for the rope, it takes around 5 to 10 interactions to reach the goal state. Our robot is also really slow, which is why we have this 4x over here. So here is a case of the cloth. So here what happens is that it starts off in being like in a folded configuration, and then it's doing this one-step MPC thing to reach the goal. Now note that over here in training time, it's trained solely on images inside a simulator, right? So we do have to use things like augmentations and randomizations inside the simulator so that these features and models are robust and they work in the actual real world. All right, so in the last section, I want to sort of go over how you can sort of train these visual representations purely in the real world, right? So in the past two works, we have seen that how inside a simulation, we can use both self-supervision and augmented data to train a better representation. And over here, what we're going to do is we're going to take those same ideas and do it just on purely real data itself. So in our visual imitation framework, what we have is a stick of this sort. So the stick has a camera on it. And so as you perform a task, it gets visual observations of the scene, right? And so once it has visual observations of the scene, what we want to do is train a model which can then transfer this policy onto a robot. Right? Now, again, our recipe over here is we're going to collect a bunch of visual data. So this is examples where a human is holding the stick and solving a task. We're going to learn a representation on this data and then just do a behavior cloning on this on these representations. So behavior cloning is just a supervised learning algorithm. So there's not much, at least algorithmically, happening over here. So let's see this in action. So we look at two robot tasks. The first one is a pushing task where the goal is to push an object into a red circle. And of course, we want to do this not just with one object in one scene, but for any object in any scene, right? So we have, I think, around 1,000 demonstrations over here, all with different objects in different scenes. Then the second task we have is a stacking task, where the goal is to pick up the object which is closest to the stick and then place it on the next closest object. And again, we want to do this on any object in any scene, right? To train this, what we do is, just a simple behavior cloning. So we have stacks of images. We feed this as input. Then we also have expert actions, which is extracted through a SFM module. So we have observations, we have actions, and then we train a simple model which outputs actions given observations as input. Now, once we have trained this model on all of the demonstrations we have, in test time, if you have a robot, we feed in the observation from the robot and apply the action that this supervised model is telling us to apply. Now, since this is a policy, you can apply this in closed loop. And so after the application of one action, you can feed the next observation as input. It will apply the next action, and it'll keep doing this until the object has reached the goal. Okay, so over here, we're going to see examples of this policy in action. So this is a trained policy in action now. In the top right, you can see examples of the frames that are actually fed as input. So this is the observations from the robot's point of view. And again, since this is a closed loop policy, I can play around with objects in the scene. And since it's closed loop, it should be able to correct for any of these sort of changes I've made or disturbances in the scene. And this also works if you're doing the stacking task. So again, I'm going to move the object around, move the goal object around, and it's still going to be able to sort of be stable to these type of disturbances. So to evaluate, we do this on a bunch of different objects, and it works fairly well across this. So I think for the pushing task, we get around 85% accuracy rates, and for stacking, which is a harder task, we get around, I think, 60% accuracy rates over here. All right. So one of the most important things in training this model is that we have to use a lot of augmentations during training. So just to show you all the augmentations that we had to try out. So here on the left, you can see what the original image from the cameras are. And then on the right, you can see all the forms of augmentation. I think one of the most interesting forms is a reflection, because when you do a reflection, you should also do a reflection of the action as well, right? Because you don't want it to apply the sort of opposite action. Now, when we actually use these augmentations, we study as well which augmentations are actually helpful. In the pushing task, we see that the color jitter is the most important one, whereas for stacking, it's the reflection and the color jitter. Both of these are the most important ones in training. But in general, we see that nearly every augmentation, it improves evaluation performance. And so if you're doing any visual robot learning stuff, it's highly recommended to try out all of these augmentations. Okay, so just to put everything together, it's a framework where I show you a few demonstrations. I do augmentation and imitation learning, and then I'm able to execute these policies on an actual robot. And here is just again the same video where you can execute these policies in closed loop. So this is the last slide. I also noticed that I'm sort of almost out of time, so I'll probably end over here.
Okay, thank you. We still have a bit of time. Questions? No question? If you want a question, probably we can move on. We'll move to the next talk, yeah, which is given by Professor Dan Negrut. Okay, let me introduce Professor Dan. Okay, so Dan Negrut is the Mid-Witter Foundation Professor in the Department of Mechanical Engineering at University of Wisconsin-Madison. And he received his PhD degree from the Department of Medical Engineering at the University of Iowa and obtained his bachelor degree from Polytechnic Institute of Bucharest, Romania. His research interests span across high-performance computing, engineering and science, the multi-physics computer modeling, simulation, computational multi-body dynamics, graphics, and visualization. And let's listen to Dan's talk on the use of simulation in robotics and AV engineering.
Okay, well, can you hear me?
Yes.
Okay,
yes, I can.
thanks for introduction. Let me see what goes on here. Okay, so bear with me 1 second. Okay, so today is Saturday, and I don't know how boring or not this talk is going to be, but I thought to myself that it would be good to start with a cartoon. And actually, this cartoon serves two purposes. It depicts me on a typical workday. Also, it goes to say that there's a lot of people that I work with, and actually they do the heavy lifting, and I'm just here to summarize some of the results that these folks are doing. And here they are. There's a bunch of undergrad students and graduate students, and then there are some non-students listed here. And as I said, I'm very grateful for them, for their work, and I just want to acknowledge that without them, this would not be possible. Some collaborators from Italy and Germany also were in the business of software development to some extent, although all of us are engineers. The outcome of the work, by and large, is software, and it's essentially the contribution of a bunch of people. I just want to say a couple of things about funding, NSF and NASA and DoD. They've been very generous and allowed us to carry on with this software development project. So the talk is going to have two parts. One is going to be an overview of Chrono, the software infrastructure that we are developing. And then part two, I'm just going to highlight two use cases, and they are related to robotics and AV, because I thought that it goes well with the topic of the workshop here. So as I said, I'm a mechanical engineer. I'm interested in solving these sorts of problems, like designing, improving designs, and sometimes controlling the behavior of these systems. Today, I'm going to hit a little bit more on this picture here, because when I said robots, what I had in mind at the end of the day was like a rover, and it goes back to why these holes are in the wheel and how it moves and such. Also, I'm interested in this kind of stuff. It's a little bit off-road, and it poses additional challenges to go through all sorts of terrains. It brings to bear interesting physics. So I have to say that I'm not I'm old-fashioned. I still struggle with this guy. You're not going to hear perhaps anything about machine learning and such. I'm just struggling with the good old m times a equals f even today. And I want to just point out the source of some of these challenges. Most of them in m times a equals f come from handling friction and contact. And the way we go about it, there are two approaches to it. One is the so-called penalty approach. Another one is the complementarity approach. This one, the latter, is a little bit more sophisticated. While for penalty, all that you need is collision detection between two bodies that come in mutual contact. the complementarity is a little bit tricky. It also calls for solving an optimization problem. And I'll come back to this. This adds an extra layer of complexity to the solution of the problem. A couple of equations. I'm not going to have a whole lot, but just kind of like the bare essentials here. This says that essentially the time derivative of the positions is tied to the generalized velocities that I use. This is the momentum balance. For all purposes, you can think of it as m times a equals force. Some forces come from joints, like kinematic constraints present in the system, which are represented here. So this is, if you use penalty, these are the equations of motion. However, if you use the complementarity approach, then you have some complementarity conditions stated here. You have the Coulomb friction model stated as through a maximum dissipation principle, which there was another speaker this morning. He touched on this, Moreau, 1973. These Lagrange multipliers, the normal contact force and the friction force, it finds its way, they find their way back into the equations of motion. So now it's a little bit more complicated problem because it's not, strictly speaking, a differential algebraic equation problem anymore, but it has complementarity conditions embedded in it. And it also has an optimization problem that needs to be solved to retrieve the frictional forces. So if you discretize this, and even when you discretize, you're not out of the woods because this is so ugly that we don't quite know how to deal with it. So therefore, we relax this discretized form of the equation of motion, and we introduce some additional term that all of a sudden renders our problem much more civilized, and it becomes a cone complementarity problem where it is like, find me the frictional contact forces that live inside the friction cone, and additionally they should be orthogonal to a different quantity that itself should belong to the polar cone associated with the friction hypercone. Now this problem looks much more civilized, but there is another form that you can cast it to. It looks something like this, an optimization problem. So we started this journey with some equations of motion, and in the end, we ended up with, okay, well, solve this optimization problem. This is a quadratic optimization problem with conic constraints. The problem is that there are two problems with it. One, it can become very large if you have a lot of frictional contact events in your system. And secondly, for some problems, the solution is not unique. It is a convex problem, but it's degenerate because this matrix is not symmetric positive, it's symmetric semi-positive, positive semi-definite, sorry. So setting aside that, let's say that we solve this. If you solve for the forces, you can do a time integration, you get velocities. You do a one-time integration, you get positions, and then you're in business. And here is, the simulation at work, the method that I just showed you a couple of slides before. This is a lot of friction, a lot of contact. The simulation is run on the GPU. It runs fairly fast. Here is what happens if you start adding cohesion between these bodies. This starts becoming called an extrusion simulation. And then moving on and getting more into engineering per se. So this problem I wanted to show here because I thought it was fun. It has to do with the problem of 3D printing. So if you want to 3D print something like this, like material like this inside of you have like a small volume, and you have like, for instance, like a piece of cloth that you want to 3D print in a small volume, then you fold it like you saw here. You fold it and you simulate first how the cloth gets folded and where each chainmail ring ends up, and then you pass this information to the 3D printer, and then when it's done, you take out the printed thing, and you end up with printed material for something like a dress and such. Here's another simulation that goes back to the penalty approach this time. If you have like a granular material hit by a projectile, there's like a wave that propagates in the material, and this is what this simulation shows. Now, in terms of like, okay, well, this looks interesting, like how fast is this? So it depends how large the problem is. Like in this case, we had like a mixer, and we went up to 123 million bodies in this mixer, and you can see here the number of hours that 3 second long simulation took, and this is the step size, by the way. One other interesting thing that this shows is that the solution scales linearly, which is good because, you know, adding insult to injury, if you don't have a linear scaling but quadratic, this would blow up. So all this is part of a software package called Chrono. Actually, this thing is a library, and you can link against it and run dynamic simulations and such. It's open source. It's on GitHub. It supports multi-physics like many body dynamics, nonlinear finite element, fluid so interaction problems. And as I said, it's middleware. We don't own the main function. You do, and you just link against our library. And it's written in C++, but it has a Python wrapper, and it runs on various operating systems with various compilers. You can be built from source, and it runs on various architectures. And we've been in this business for a number of years. There'll be a release 6.1 soon, and there's some information in case people are interested in having access to the software. Okay, so here are some examples of engineering type that we run with this software. Here, for instance, is a simulation of a track vehicle moving on a side slope and understanding how fast it can drive and still avoid an obstacle without spinning out of control. There is like nonlinear finite element tire operating on granular terrain. If you put 4 of these together on a vehicle, and you want to see how the vehicle negotiates obstacles, this is, by the way, it looks interesting, but it takes a pretty long amount of time to finish something like this. So this was basically kind of like rigid and flexible body dynamics, but I want to bring into the spotlight here also the equation motion for the continuum, because I'm going to use that when I talk about the test cases that I'm going to show at the end. So this smoothly particle hydrodynamics approach handles a continual representation of a material, and it can be a fluid, or it can be, as you will see shortly, a solid. And we're using here, it has been used for a lot for handling fluids, but here we're going to use it to represent granular terrain, which by and large is discrete, through a continual representation. So here we have the good old balance laws for mass and for momentum. And if you look at the unknowns, well, we don't know what rho is, we don't know what U is, and we don't know what sigma, the stress is. So we have 2 equations, but we have 3 unknowns. So we need some sort of like more information. Well, we can split the Cauchy stress tensor into an isotropic pressure and a deviatory component of stress tensor. We haven't done anything yet useful. We just like massage things here. But here is one other equation that can help, and this is the Zaremba-Jalman equation that tells me how the stress changes in time. And if I use this in conjunction with the other 2 equations, then perhaps I'm in business. Now, there are still some variables here that might throw a wrench in the works, but it turns out that the rotation rate tensor depends on the velocity. And then I have this fellow here. Well, this is defined and as the Zaremba-Jalman rate of the Cauchy stress, and it has an expression that depends on some material constants, and it depends on the strain rate, which also depends on velocities. So in the end, I have a closed problem. I have to amend the strain rate if I have plasticity, because the material starts flowing. But at the end of the day, this tau, it was introduced on the previous slide, so it's a friend of ours. Long story short, I have a well-defined model that I can solve. the way we solve it is through using smooth particle hydrodynamics, XPH. And there are some tricks of the trades. I'm not going to spend a whole lot of time. I just want to point out that there is an inconsistent method that preserves angular momentum, or there is a consistent method that is a little bit higher order but does not preserve the angular momentum. We use this one. It's second order, and we use this one. And with this method, we discretize our equations, the mass balance, the momentum balance, and here is the equation that gives me the time evolution of the stress. So with this, I'm in business. I have a solution almost, because I have to talk a little bit about the coupling between, like, for instance, if I have a rover like this one here and I have granular material, I need to say like how they work together. And we have what is called like boundary BC particles or markers, boundary condition enforcing particles, which are, you can think about them as fluid particles that are rigidly attached to the rigid bodies, so that they provide the boundary conditions, like no slip conditions, associated with the interaction between the fluid and the solid. So then we have a co-simulation. This part of the system, the rover, is solved with the equations that I showed probably like 20 slides ago, while the time evolution of the terrain is solved with the equations that you saw 2 slides ago. Now, there is one thing that needs to be discussed. The stress needs to be handled carefully, because you have plasticity here, and sometimes the material behaves like an elastic medium, but sometimes it starts flowing. And there is a guess, a predicted value, and then you compute a deviatoric stress tensor. And you can think about this like a normal force, mu static times the pressure. And just like you have in reality, if the friction force is less than the normal force, and you know, a little bit of hand waving, but that's how you can think about it from a high vantage point, then if this condition holds, then essentially you guessed right. If not, you relax the value of the deviatoric, the shear deviatoric stress tensor, because it cannot go beyond the friction, outside the friction cone. You project it back on the cone, and then the material starts flowing, and you maintain the pressure, but you scale back the shear stress. So that's that. Now I'm going to show you some simulations in the beginning. They have to do with the fluid, the same equations, but the plasticity doesn't come into play here because they are just good old Navier-Stokes equations. This is like, for instance, the Fording simulation. And again, some of the equations are the rigid body dynamic simulation equations. Some of them are the fluid that I just showed some slides ago. And finally, this is one that shows the granular material represented as a continuum, and it shows the Viper rover moving over obstacles or climbing up a hill and such. And this is a nice segue into the second part of the talk, where I'm going to touch on the simulation in robotics and AVs. So let's do first the simulation in robotics. This project that we're working on is actually a small sub-project of a bigger project that has to do with the Artemis mission. NASA wants to establish a base camp on the moon, but first they want to send the Viper rover in 2023 to the moon to look for frozen water, because they need water to live there. They don't want to hold it from the Earth. So our small piece of the action goes back to simulating the rover mobility for traction control. And if you remember, I told you that the traction, I showed you that picture with some holes in the wheel. They want to avoid those holes, and they want to avoid the vehicle getting stuck. When it comes to machine ground interaction modeling, they're like, by and large, kind of like 3 levels of complexity, speed, and accuracy, so to speak. Like, this is very fast, but is empirical. This is what I showed you like 10 slides ago. And this is what I didn't show you. It's kind of like taking that simulation, the granular, the fully resolved granular dynamics, and putting the vehicle on that material is highly accurate, but is extremely slow. So I'm going to focus on this and using the equations that I just showed you 10 slides before. So here is a simulation of the rover moving over rocks. And the idea is to, how should you control the angular velocity of this rover to avoid here in the right corner here. What happened, people figured out that Curiosity was getting like big holes in its wheels, and they had to do with the fact that the rover was driven with constant angular velocity at each wheel. So the problem is like this: when the first wheel travels above a rock, it has to travel a longer distance. So in theory, it should rotate faster than the rest of the wheels, but this was not the case. So what happened is like the other 5 wheels were jamming the 6th wheel into a rock and dragging it over the rock. And you know, it might not sound much, but here is in the right upper corner, this is what that led to. And there's another story that is interesting. One of these rovers, there was 2 sent out and one got stuck. I don't know if you remember, but it just got stuck and it couldn't get out and it died there. So that's the purpose of this traction control. And here is the continual representation of terrain using that SPH. Just to put things in perspective, this is on flat terrain and the number of particles is 2.5 million. The step size is here. The particle size is here. The simulation time, this was for 20 seconds. It ran on a GPU Ampere A100 and took about 4 hours. And the real-time factor is 720. So it means that 1 second of simulation essentially takes 720 seconds of compute time. Real time is an RTF of 1. So that's just to put things in perspective. Here is the simulation that we care about in this project. And take a look at the wheels and see what happens like here when these wheels get there. So this is what you want to control. You want to understand how you should turn these 6 wheels, because they have independent electric motors. You can control them any way you want. So the question is, how do you do that so that the rover moves up and saves battery? And just to give you an idea about like what you can get out of this, here, if you move, you want to move from point A, the bottom of the hill, to the top of the hill, and we can do it one of 2 ways: just maintaining blindly all the angular velocities constant, or changing the angular velocities of the wheels as they start climbing and they start hitting the horizontal plane. So this is in the right corner of the simulation. You have some dimensions here, and I'm not going to get into what the control policy was and how we picked it. But long story short, in the first 5 seconds of motion, it saved 18% of the energy, the battery, and all the way from this point to that point, overall, it was 8% energy saved, because you just decide to send different amounts of torque to different wheels. And this goes to show some plots. For instance, here is the control off, the slip ratio. It's all over the map. By the way, a negative slip means that the wheel is dragged, and that's, you don't want to have that. You don't want to drag a wheel. You're just bulldozing. That's a bad idea. And here it's again negative slip. These other control on, as you can see, all the wheels have the same slip. And if you look at the torque varies much more wildly. Like, look, at some point you brake, and why would you do that? Also, this is the amount of power that it's needed to move the rover up with constant angular velocity. And this is the amount of torque that is needed with this control policy. So, long story short, you can gain things if you can save battery if you move in a certain way. Okay, moving on. I have 6 minutes here. Simulation for human in the loop and AVs. So what's what's this project about? So the project has to do with understanding the interplay between autonomous vehicles and conventional vehicles. Now, a conventional vehicle in this project, an autonomous vehicle can become a conventional vehicle when the human freaks out or gets bored or whatever and decides to assume control of the command. And the question is, that's not my question. There are some people who do human factors. I'm just with the simulation part. But the question is like, why does the human freak out, or when, and what happens then in terms of like the overall traffic? What sort of like outcomes, fallout happens because the human all of a sudden decided to assume control? And the idea was to have like a simulation of 30 miles. We've never simulated anything like that. Our simulation is like 20 seconds, half a minute. It was like 30 miles, multiple vehicles engaging platooning, and all of a sudden you hear about the driver experience, about sounds, about the feedback in the steering wheel. And these simulations, as it says here, they sometimes are expected to last like 30 minutes. So how we went about this to maintain real time, having like multiple vehicles, we developed like an infrastructure, like an Uber simulator. We call it Synchrono. So it's synchronously running multiple chrono simulations. So you have like every single vehicle is basically a simulation. Now these simulations running at the same time in this Uber simulator, they have to be time coherent and space coherent. And we're interested in physics-based, accurate. We want it to be modular and we want it to be scalable, to be able to run, for instance, like tens or hundreds of vehicles in one scenario. And here is like, just as a benchmark, we looked at, okay, what's the performance of this if we take the simulation and put it on deformable terrain, because it's significantly slower than driving on rigid flat terrain. And here it shows that the real-time factor RTF for like 27 vehicles, it's still it's faster than it's lower than 1, so it's faster than real time. So we have to simulate the sensors, and there are proprioceptive sensors and some exteroceptive sensors like GPS, camera, lidar. So we have models of these, and we have models of virtual worlds, mostly done in house. Some of them we piggyback Carla and LGSVL in terms of like assets. These like the vehicles that we're using in these simulations, and I hope that this runs is yes, it's just like a snapshot of a person in the simulator and the vehicles. There are 13 vehicles in this setup, and the student is driving. It's a small neighborhood out of San Francisco, and this is taken from the LGSVL library of assets. So essentially, you can have like a bird's eye view. You can see what the driver sees and monitor what he or she does. I really like that Jay looks over his right shoulder. He's a really good man, He was told that when he changes the lane, he should look. Basically, there's nothing there, but just like he grew up like that, so he does it. And I was telling you about the sound. You have to, when you rev up, you have to hear the sound the way it is, and when you turn the wheel, you should have in that operation some feedback, just like in the real car. Now the idea is that we want to also by the way, the simulation I showed you before was done like a third floor in the mechanical engineering building, the driving simulator, and fourth floor where the cluster ran. We also worked on an infrastructure in this Synchrono to simulate with the human in the loop at the University of Iowa at the National Advanced Driving Simulator. This is like an $80 million facility. It's okay. We're not there yet, but we're working on that. And lastly, this has been also, I don't know if this is going to run or not, but Chrono is also embedded in Carla. It's one of the dynamics engines that are available if you want to drive the vehicle. Okay, I'm going to move on. Looking ahead, we want to increase simulation speed. Flex bodies are slow. Machine gun interaction is relatively slow. And also deal with the sim to real gap. And here, what we're doing, we're building. We cannot afford to have like full vehicles and such right now. Although next year we'll probably get one from GM. But right now, what we do, we have this vehicle here, and we have a Chrono model of it, and we run them side by side with a unified, the same autonomy stack. It's a ROS2 based autonomy stack. And we want to understand if the policy fails to transfer to reality, why that is. And to that end, we want to have like the same autonomy stack running on the actual vehicle, the same autonomy stack, we want to have it running Chrono. So that's that. I think I dumped a lot of information on you here. I just want to say thanks a lot for taking the time on a Saturday to come and listen to my talk. And I don't know if I have time, but if I do, I would really, love to answer any questions you might have. So thanks for your time.
Okay. Wonderful talk. So I mean, because of the like Saturday time and the virtual meeting, many of the audience that should be interested in our topic may not be here, but fortunately we're leading the recording of the talks. So I'm confident there will be like many more people seeing this wonderful.
No worries. Okay, so I'll stop sharing at this point.
Maybe we can have one quick question. Bambo, do you have a question? Okay. One question that I have is is there a plan to make the simulators differentiable?
Honestly, we just submitted the proposal on that. And so it depends on that. If that proposal gets funded, the answer is yes. If not, then probably not. Because it's not going to be a stroll in the park to make it differentiable. There's a lot of stuff. So it depends on that. But yes, we're interested in that.
Okay, great. Maybe for the sake of time, we'll have to move on.
Yep.
We will start. Yeah. We'll start the spotlight session. And I have to give a talk in another workshop, so I might leave and handle the host responsibility to Fanbo. Hey, Fanbo.
Oh, hi.
Hey.
I have to set up, right?
Okay. Okay.
Okay. Okay, yeah. So, hi, I'm Fanbo, and I will be handling the spotlight presentation section. So let's get started. For the spotlight presentation section, we have invited researchers to talk about their recent works. So first, let's welcome Fabio Ramos from NVIDIA to talk about a Bayesian perspective on the sim-to-real gap.
Thanks, Fanbo. Can you hear me okay?
Yeah.
All right. I hope you can see my screen.
Yeah.
Perfect. All right. Let me start this talk by going back to 2008 and giving you a bit of a perspective of where we were in terms of automation. So a big mining company came to us that's in Australia and said, look, guys, I would like you to automate this entire company, right? All these machines, these big trucks, these drills, this large piece of equipment. So each truck is about 200, 250 tons. And I want you to turn these machines into robots. And we said, okay, that sounds fun. Let's start doing it. The first machine we decided to automate is probably one of the most boring ones. Is this thing? It is a drill. It's a drill that essentially makes holes in the ground where you fill up with explosives and you blast to break the rocks in the ground. And this is a iron ore mine, right? Essentially, you break these rocks, you excavate, put into trucks, and ship that to Asia. So this is the first machine we automate, and obviously we build good simulators for this. Then we said, okay, what's the next machine we want to automate? The next machine was this. It was a truck, and this is one of the cool things you can do as a PhD student in Australia. So here comes the truck, and we said, okay, let's automate the truck. Here we stop. It didn't. So we actually realized the sim to real gap and the dangerous tasks that we were trying to solve were actually pretty significant. So we had to be much more proper in how we design policies and controls for that. So a few years passed, and we decided to, do proper statistics to understand the reality of the problem, the uncertainty of the problem, and how we could capture all of these into models that would be reliable and automate this entire industry. So one of the first things we did was fusing different sensors. So these are laser scans, GPS, to come up with a terrain model of the area. This is one of the terrain models we obtained. And with this terrain model and correcting with the proper uncertainty, we're able to turn all of these machines and actually a major part of that company, of that industry, into a fully autonomous industry, where you see the trucks, the drills, all moving around autonomously and delivering a lot of these minerals to other countries in Asia. What you see here are the autonomous trucks that are now operating. And if you're interested in the full coverage of this story, you can go to YouTube and then type BBC Rio Tinto autonomous mine, and you'll find all the details of what's going on in there. Now, to actually make this stuff work, all of these things work, we had to address a few principles. And I carry on with these principles to today, but I'm going to briefly describe these things here. So one of them is, well, it's very important that when we put a model, and you see that the model there is the black curve in there, and we have data, the uncertainty should grow. Our prediction should, the uncertainty of our prediction should grow in areas where we don't have data. So that is really critical, because it tells us how wrong we might be about what we are trying to predict. The other thing we want to do is making sure that when we don't have data, the function goes back to its mean or its prior. And you see that's exactly what happens there. So you know that these models that we predict go back to a specified behavior when we don't have data. The other thing we want to like to do is to incorporate biases, inductive biases, and other things like this that actually allow us to clamp the behavior of the learnable function whenever and each place we want it. With these principles in mind, I started at NVIDIA, and we said, well, can we then extract these ideas to then build better simulators, and simulators that understand the statistics and the uncertainty of the real world, and combine these simulators with policy learning algorithms like RL. So what I'm going to describe today is one approach to do that in a fully Bayesian way. So let's say we have a bunch of simulators. They can run different simulation. And when we run a simulation, this is called forward modeling. They allow us to see the behavior, the simulator behavior. We can then have access to the real data. It might not be, this might be just, a very few rollouts of how things behave. And we are interested in inferring the parameters of these simulators based on the real data with the connected uncertainties. Once we have these parameters, the simulator will understand the real data. So we design what is called the Bayesian. That's an algorithm that you guys can see and get the details for that. But essentially, we put priors over simulation parameters. We then simulate multiple times. learn a model, learn the basic model, plug the data, and recover the posterior. With this posterior, we can then use domain randomization, which is a standard technique in reinforcement learning, to learn better policies. All right, that's the idea, the cross idea, and you can essentially do that multiple times. We estimate the posterior, visit the real world, collect another rollout, and carry on improving our uncertainty and our estimation of what happens. I will, for the interest of time, just go to a few, one example. So this example, we are trying to infer the properties of granular materials. And the idea was, we take pictures of the structure of the granular materials, after going through this funnel. And then we try to optimize the policy. The policy in this case is just the height of that funnel to make sure that we recover a specific pattern of this. And I will be finishing in a second, Fambo. So for example, here is the different patterns we see as we pour granular material through this funnel. And as we go on and train the simulators through basing, capture the uncertainty of the parameters, we can then translate that to the real world, and that's what you see there. All right, so I want to make a few comments that we are now extending some of these ideas to differentiable simulations. And this is a fully differentiable simulator for robotic cutting. And these allow us to infer parameters of the cutting process, all kinds of strength in this material. And once we learn that, we can then perform this, observe this in the real world, collect the rollout, and estimate the parameters of the simulator as we go on. All right, this is the work done by Eric Hayden in our lab. Basing code is available to anyone who is interested. Basing IG, so it's fully connected to one of NVIDIA simulator called Isaac Chim. So in summary, we are trying to bring models and prior knowledge to RL, so to learn policies in simulation that would nicely translate to the real world. One way of doing this is by running multiple simulations in parallel. Basing does that while assessing the uncertainty of this process and capturing where the simulation might be wrong about this procedure. Thank you to all my collaborators, and I'm happy to take your questions.
Yeah, hi. Since we're short on time, I think if there are any questions, maybe you can type in the chat window. Thank you, Fabio Ramos, for a great talk. Let's move on to the next presenter. So next we have Jiafei Duan from Nanyang Technological University of Singapore on space, a simulator for physical interactions and causal learning in 3D environments.
Yeah, thank you, Fambo. Let me share my screen. Are you able to see my screen?
One sec. Okay, yeah. Okay,
cool. Yeah, so hi everyone. My name is Jiafei. I previously was from Nanyang Technological University. Now I'm a research engineer at A*STAR, Institute of Infocom Research. So today I'll be presenting on our work, which is on space, a simulator for physical interaction and causal learning in 3D environment. So here's the outline for my presentation today. And the motivation is simple. So this is a picture of me back then, those carefree days playing pool. So from this picture, what can we infer? We can actually infer that humans have the ability to sort of predict a certain form of trajectory in terms of how physical interaction will occur in the real world. And as much as we want to believe that we are good at playing pool, but the matter of fact is not that. The matter of fact is that actually this is all thanks to our naive physics, which is the ability that humans have innately to actually predict this kind of physical interaction in the real world. So the motivation is simple. Our ability to predict physical interaction it's still a topic that's debatable in terms of what is the actual approach that we are using. But as an embodied intelligence, which is a child, since young, they are being taught, or sort of like there is a form of real world data set that is shown to them in order to help them to learn this type of features of predicting physical interaction. So for them, you usually start off with a form of a simple block cube and not really like a transformer toy, which is too sophisticated for the child himself. So with that in mind, we actually propose our work on space. But before that, let me share with you some of the related work in this field. So some of the related work in this field are, for example, Cleverer, which is from Professor George Tenenbaum's group, whereby they focus on synthetic video data set generated out of a simulator, which covers about 300K QA data sets for causal reasoning, or even co-physics that focus a lot on the causal reasoning of counterfactual learning. And also we have Carter, which is a data set that actually work similarly to using 3D synthetic video to actually focus on long-term reasoning. And moving forward to our data set. So the space data set actually is generated out of the space simulator. And this has been a recent trend in the vision community, whereby to actually synthesize data set in a 3D environment and generate the 2D video, synthetic video of that data set. Of course, there's a lot more advantage in doing such approach, because you are able to get the ground truth, the meta information, and also it allows you to vary across different varieties of object class. For our case, we have a total of 7 object class and different containment holder. So for our data set, it actually consists of 3 parts, of 3 basic physical interaction on stability, contact, and containment. Of course, we also obtained all the visual attributes that's necessary for the data set. And all this is done through the Python API on Blender. So moving one step forward, we did some form of analysis on the data set itself. We collected about over 115K video data set, synthetic video data set, over 2 million frames. And we analyzed the data set based according to its outcome, whether will it be able to be stable, contacted, or contained. And of course, I can see that it's not really a very balanced data, because this is actually based purely on the realistic physics engine from Blender itself, which is the bullet engine. So with that, what we are trying to show is that can we train an AI model using an approach of a curriculum-based learning, whereby we start off with something simple and translate it into a real-world complex example. So for that illustration purpose, we actually use the iconic UCF101 dataset, which is a collection of sports and action video frames. And from there, we actually sample only 3 classes based on the fixed camera angle, and that each of these classes contains at least two modality of our space data set, be it contain or contact, or containment or stability. So with that, we actually sample a total of 330 total video data set for training purpose. And using curriculum-based learning, And using curriculum-based learning, we actually deployed the state-of-the-art physics-based deep model from last year's CVPR, which is physics DNet. And we show that by just using only first five input as the input sequence, you are able to use physics DNet to generate the subsequent 45 frames. And using the idea of curriculum-based learning, we train on 20 and 30 for pre-training on space and fine-tuning on space and UCF3. And we have shown that by pre-training with our space data set, we actually can increase the generative performance on the UCF real-world data set. And this proves the point of curriculum-based learning, that we should start off with something simple for the learning of physical prediction. So with that, come to the end of my sharing, and hopefully thank the organizer for the opportunity. So to summarize what I just said, space actually is a 3D simulator for synthesizing physical scenario in 3D environment, and we collected a large-scale synthetic video data sets of 3 physical interaction. And we have also demonstrated the impact of curriculum-based learning using such a fundamental space data set for training state-of-the-art physics prediction deep models. So thank you, everyone. I'm open to any question.
Hi, Jiafei. There was a question
in
the chat saying, can you elaborate more on how curriculum-based learning is used? what's considered simple?
Okay, so for example, algorithm-based learning is used in terms of the kind of data that we are actually using. So as compared, as mentioned previously here, of course, as you see that the UCF is a much more complicated real-world example. And if it encapsulates a certain features of the physical dynamics, this high level physical dynamics can actually be learned through the model first being trained on low-level physical dynamics, such as a space data set, which focus primarily on the physical interaction itself, rather on the human attributes. So that is what we define as the curriculum-based learning in this approach. In fact, we have an extension work that is in the pipeline actually under review that will focus more on extracting the physical dynamics itself within such frames. Yeah, hopefully that can answer the question. Yeah, thank you.
Okay.
Yeah, thank you, Dr. Nicer.
Yeah. Thank you, Jiafei.
No problem.
We can move on to the next speaker. So let's welcome Ming Lin from New York University on the topic of V2X-Sim, a virtual collaborative perception dataset for autonomous driving.
Hi, can you see my screen now?
Yeah.
Okay, cool, thank you. Hi, I'm Ming. I'm a second-year PhD student at NYU. Today, I'm very happy to present our work, V2X-Sim, a virtual collaborative perception dataset for autonomous driving. And this is a joint work with Zian from NYU, Yi Qizhong from University of Southern California, Professor Chen Siheng from Shanghai Jiao Tong University, and Professor Chen Fen from NYU. Recently, single vehicle self-driving has been intensively studied, and there are many single agent perception datasets have been proposed, such as Kitty and NewScenes. However, long-range perception is challenging due to the sparse measurements of 3D sensor, especially at a long distance. Meanwhile, individual viewpoint often suffers from frequent occlusions, which may result in safety issues. So in this background, V2X, the concept of V2X has been proposed, and vehicle to everything denotes the communication between a vehicle with other entities participating in the traffic scenarios. So through such collaboration, the single agent perception issues such as long-range perception and frequent occlusion could be fundamentally solved. And V2X includes both vehicle to vehicle and vehicle to infrastructure. And according to the estimation of US Department of Transportation, if a V2V system were implemented, there will be 439,000 fewer crashes every year. However, in current community, there is no public collaborative perception dataset, and collecting such a realistic collaborative perception dataset is really costly. And simulation environments can help generate large-scale datasets with free and well-annotated ground truths. For example, color is widely used in the autonomous driving research. Most importantly, synthetic datasets can support the cutting-edge research before the realistic data are readily available. One typical example is here, high-density long-range point cloud sensor proposed in all-in-one drive dataset. So in this work, we use Color Sumo co-simulation to generate our perception, our multi-agent perception dataset. And Sumo is firstly used to produce numerically realistic traffic flow, and Color is then used to retrieve multimodality sensor streams from multiple vehicles at the same intersection. And we collect data from 3 towns in Color. We attach multimodality sensors onto each vehicle, passing through the same intersection at the same time. We also attach multiple sensors onto the roadside infrastructure. So our dataset can enable both V2V research and V2I research. So in summary, our dataset has several features. The first one is multi-agent recordings. We provide well-synchronized recordings from both roadside infrastructure and multiple vehicles at the intersections. Here are four views of 4 agents. And here is the 4 camera views of the same roadside infrastructure. Secondly, we provide multimodality sensor suite with RGB camera, LiDAR, GNSS and IMU. Thirdly, we provide diverse annotations, including semantics label, depth ground truth, and 3D bounding boxes to enable various downstream tasks. here is some visualizations of our dataset in bird's eye view. In each figure, a different color denotes a different agent. And these agents are used to collaboration with each other. And the gray color denotes the measurements from the roadside infrastructure. And the orange box denotes the vehicles in this intersection. And we follow the format of the widely used nuisance dataset to make our dataset more useful. And we also provide a tutorial in our dataset website. To conclude our work, we propose the first public multi-agent perception dataset in driving scenarios. And our dataset can support various downstream tasks, including collaborative detection, tracking, and segmentation. In the future, we seek to simulate more realistic data, including latency and sensor corruption. And we will also try sim-to-real domain adaptation to make our dataset more realistic. Finally, I want to advertise our recent work, DiscoNet, learning distilled collaboration graph for multi-agent perception, which is accepted by Negrut 2021. In this work, we use the V2X sim dataset to verify our algorithm. And we also provide benchmark results for the state-of-the-art collaborative perception methods, including V2VNet, One2Come, and Who2Come. And then we plan to release our code and dataset at the end of this month. And you're welcome to check our website and our code if you are interested. So that's all. Thank you.
Thank you, Yiming.
Thank you.
We have some time to take some questions. Okay. Yeah, if there are no questions, we can move on to the next presentation. Easy. So next, let's welcome Qi Wu from UCLA to talk about GSTOR, communicative learning with natural gestures for embodied navigation agents with human in the scene.
Yeah, thanks, Fanbo. Hi, everyone. So can you start sharing my screen? Okay. Get started. Okay. Hi, everyone. I'm Chiu from UCLA. So I'm going to present our new work on the communicative learning with natural gestures for embodied navigation agents. This is the overview of this presentation. So I'll start from the background motivation of our work. So gestures form a nonverbal communication with visible bodily actions and play a significant role not only in human-human communication, but also in human-robot communication. Let's take the following case as an example. So here our task is to instruct the robot to clean the circled area. And to complete this task, the human player and the robot must have the joint attention on the target. And here the question is, how could we convey such a message to the robot? And in a language-only scenario, in order to refer to the exact location, we call lengthy text to express our intent as shown in this example. And in contrast, gestures allow to express the same messages in a much simpler and more natural way. So for example, we can say clean here while pointing to the target location. In this way, the human message could be correctly interpreted with a joint understanding of the scene and the semantics of gestures. Inspired by the significance of gestures in human-robot communication, so we intend to bring nonverbal communication cues into the embodied navigation task. We contemplate on a few questions, and ultimately, we want the agent to solve two problems in our framework, so multimodal target inference and navigation. We think they should be mutually beneficial, that is, learn to communicate and communicate to learn. So before we talk about our work, so let's take a look at some previous works. And visual navigation has made significant progress in the last few years for the embodied agent with advances of deep learning models and also the simulated environments. Advances in vision and language understanding have enabled visually grounded language navigation agent to be trained. Those works are referred to as vision language navigation, or VLN. So including instruction following, embodied question answering, and so on. Despite using verbal cues for the visual navigation, there are also existing works incorporating other modalities, including target images, semantic priors, acoustics, and so on. Here, our work is built on existing VLN framework, but extended by incorporating gestures as a new modality for communications. Gestures have been widely used as a communicative interface between human and robots in robotics. So prior literature typically predefines gestures with their meanings. So for example, this OK signs means approval. And in our work, we want to develop a flexible system that could uncover the semantics of natural gestures without predefining their meanings. So to summarize, we developed a simulation framework that supports multimodal interaction with human users and demonstrate that the embodied agent could improve its navigation performance with gestures and understand the underlying semantics. So in this section, let's talk about more details of our simulation framework. So this is an overview of our framework, and it's named GestSOAR, so which is shorthand for gesture-based SOAR. In this framework, the human players could interact with the simulation environment where the AI tool environment and multiple sensory devices reside. This environment could generate observations from different modalities. Those observations are sent to an aerial planner to generate sampled actions. And let's break down this framework to see how each component works. This is first part. So as the name of our framework indicates, we build our simulation framework based on the ISO environment named AI tool SOAR in Unity. Aside from that, Unity has good compatibility with different sensory devices. So we integrate Oculus Rift, Connect V2, and Leap Motion controller with our environment to enable human-robot interaction. Let me give you one example here. So this example shows how those devices work simultaneously in this VR environment. Oculus Rift immerses the human players in the virtual environment, while Connect V2 and Leap Motion tracks the body and hand motions. In our data set, each task is defined with the environmental information and gesture information. In this example, the task for the robot is navigating to the chair from its initial position. We have two types of gestures to instruct the agent. So one is called the referencing gesture. The human player communicates with the agent to guide the direction, for example, pointing with a finger. The other one is called intervention gesture, and the player shows gestures in a rejecting manner used to warn the agent if it is moving away from the target. So the motions of the human players are saved as a sequence of features. Each frame contains the positions and rotations from different track joints, and they're encoded as a feature vector. So here are some examples of our recorded gestures in different scenes. Our dataset contains a diverse collection of referencing and intervention gestures covering different room types and object types, and they will be used for our navigation task. So in this chapter, we will go over our navigation task and the learning network. So in this work, our agent is required to reach the target object in a simulated environment with different observations. So in order to succeed, they must navigate to the proximity of the target, look at it, and issue the stop action. And we allow multiple stops in our simulation environment. So the learning process could be formulated using deep reinforcement learning. And specifically, we take proximal policy optimization as our RL training algorithm. So this is the learning network architecture. A joint feature vector can be obtained by concatenating different encoded observations. The joint vector is passed to a memory unit to encode the history, and the active created model samples the action for the agent to take in the environment. This section covers our experimental results. So we use two metrics to evaluate navigation performance: success rate and success rate weighted by path length. So we use three methods for evaluation: baseline, reference gesture, and intervention gesture. Those two charts show the navigation performance as a test set for different methods measured at the first stop. So you could see that using gestures, we perform better than the baseline methods, of which the intervention gesture is a more effective kind of gesture to instruct the agent. This table summarizes the performance of agent with different number of stops, and we can see that with higher number of stops, so our agent performs better with the gestures compared with the baseline methods. To visualize the effectiveness of our method, we show some qualitative results here. So compared with the baseline method, where the agent only often struggles to find the target, our referencing gesture model enables the agent to navigate to the target more intelligently. And as to the intervention gesture model, our agent is able to understand the gesture and react to it by rotating until it faces target object before moving forward. Here, I will give you some examples to illustrate the human inference with human and scene. Here is the example for the user is situated in a virtual environment and gives the agent a direction to the target object in the room using gestures. Body and hand key points are detected by connect and leave motion and pass to the agent. The agent sees the gesture and starts navigation in the room until it reaches the target destination. This another example with intervention gestures. The agent starts navigation in the environment and the human user instructs the agent in the rejective manner when it intends to move in the wrong direction. The agent understands this gesture and turns in the correct direction until it finds the target. So here are some conclusions and the future work directions for our project. So to summarize, our work is the first incorporating human gestures for embodied agent learning and show the agent can learn the semantics of gestures without supervision. And there are some future works, including adding more objects, defining more complex tasks, and we can even allow the agent to show gestures in response to the human players. Thank you. And I'm welcome to any question you have.
Thank you, Qi. We also have to take questions from the chat window. We can move on to our final spotlight presentation from Qirui Wu from Simon Fraser University on plan to scene, converting floor plans to 3D scenes.
Hi, everyone. Can you see my screen?
Yeah.
Okay. Hi, I'm Qirui from Simon Fraser University. I'm glad to be here to present our work accepted by CVPR 2029. Plan to scene, converting floor plans to 3D scenes. Digital 3D scene representations of interiors have a variety of applications, such as the virtual walkthroughs of real estate listings, previews of products placed in a room, and training AI agents in 3D simulators. However, these 3D scenes are usually created through intensive manual design or imperfectly captured using depth sensors and 3D reconstruction techniques. Neither of these approaches are readily usable by inexperienced users. Usually, real estate websites often provide floor plans and associated photos of residences. Prior work has used precise camera view estimation to project these photos onto walls, but this approach cannot handle surfaces not seen by photos. And objects such as furniture or are unrealistically projected onto walls. Our work addresses these limitations. We introduced the new task of plan to scene, converting floor plan to and the photos of a residence to a textured 3D mesh of a house. Now I'll go over the whole pipeline of plan to scene. Given a floor plan image and the photos of the house as input, a floor plan vectorization approach detects walls, doors, windows, room types, and fixtures from the floor plan. We lift the vectorized floor plan into 3D using a rule-based approach. And we place CAG models for fixed objects in the floor plan. The photos of the houses are assigned to the rooms. And then we can detect the surfaces in photos and rectify them. Next, we extract the crops from these rectified surfaces. We condition on embedding-based texture synthesis approach on these rectified surface crops to synthesize a texture crop for each photo observed surface, which can be tiled and applied as a texture. Since multiple crops can be extracted from a single surface, we use a texture needs score based on VGG statistics to determine the best surface crop for texture synthesis. Next, using a graph neural network, we leverage inter-room and intra-room consistency trials to generate tileable texture crops for unobserved surfaces. The final output is a textured 3D mesh models of a house. In this paper, we focus on texture generation and propagation and assume other steps are given or handle them with simple approaches. So a key challenge in plan-to-scene task is to operationalize what constitutes a good texture. A good texture should capture the substance, color, and pattern of the surface. In addition, the texture should be tileable. A tileable texture does not show seams when tiled, and also does not look notably repetitive. Using our approach, given an input surface crop, we can generate the textures that captures the 4 properties I mentioned before, and corrects for illumination and other artifacts in the crops. And now I will provide more details about our approaches. For texture synthesis, we adapt a texture synthesis approach from prior work to suit our task. We introduce a substance classifier during training to encourage a structured latent embedding to improve better color similarity. And we switched to HSV color space and separated the median color and the offset color, aiming for disentangling color and pattern. Since we sample many crops from photo observed surfaces, we choose an optimal crop using a texture needs score to condition texture synthesis of observed surface. For propagating embeddings for photo and observed surfaces, we use a graph representation where the nodes represent the rooms and edges represent room-door-room connectivity. Then we use GNN based on gated graph convolution to predict texture embeddings for photo and observed surfaces. Now let's look at our results. We compare against 3 baselines here. Texture retrieval-based approach, and the direct use of a crop sampled from a surface, and a naive application of neural texture synthesis. To perform a quantitative comparisons, we define a suite of metrics to measure. One is how well a texture matches properties of the input surface, such as color, pattern, and substance type. And also the tileability of textures. We also how well the texture set distribution matches the input surface distribution. For all these metrics, the lower values are better. So in this evaluation table, we can see our theme method outperforms other baselines on both observed and unobserved surfaces. And the retrieval approach is quite competitive and even outperforms the naive scenes on many metrics. For this crop one, it does well on this similarity metrics by virtue of directly using reference crop as a texture. However, it obviously does not produce tileable textures as seen by these high tile metric values. Here I will show you 3 examples of qualitative results. Our approach textures observed and unobserved surfaces plausibly texturing the whole house. We also conducted a user study, and we asked the users to choose the best in this in hours versus baselines choice setup. So for each study example, we presented 2 versions of textured houses to users. One is hours method, the other is one of those baseline methods. So about 70% of user study participants preferred our proposed method over alternatives. So thank you for listening. For more information, please refer to our website. We provide supplemental material, code, pre-trained models, and also the data sets. Yeah. Any questions? Yeah.
Yeah. Thank you, Siri. So we can take questions again in the chat. Let me see. Okay. Let me start my sharing. Okay, so next, we will move on with speakers. So first though, we will have Professor Karen Liu to talk about AI augmented physics models, and I will first give an introduction for Professor Karen Liu. So Liu is an associate professor in the computer science department at Stanford University. Prior to joining Stanford, Liu was a faculty member at the School of Interactive Computing at Georgia Tech. She received her PhD degree in computer science from the University of Washington. Liu's research interests are in computer graphics and robotics, including physics-based animation, character animation, optimal control, reinforcement learning, and computational biomechanics. She developed computational approaches to modeling realistic and natural human movements, learning complex control policies for humanoids and assistive robots, and advancing fundamental numerical simulation and optimal control algorithms. The algorithms and software developed in her lab have fostered interdisciplinary collaboration with researchers in robotics, computer graphics, mechanical engineering, biomechanics, neuroscience, and biology. Liu received a National Science Foundation Career Award and the Alfred P. Sloan Fellowship, and was named the Young Innovators Under 35 by Technology Review. Liu also received the ACM SIGGRAPH Significant New Research Award for her contribution in the field of computer graphics. In 2021, Liu was inducted to ACM SIGGRAPH Academy. Yeah, let's welcome Karen Liu for the presentation.
All right, thanks. Well, thank you for the introduction. Should I use my own slides? Share the screen? Is that how it works? Yeah. Okay, all right, then I'll do that. I'll do that right away. Okay, can you guys see my slides?
Okay, perfect.
Cool. All right, thanks for the introduction, Fembo. Like you said, I was working at the intersection of computer graphics and robotics. Like the first part of my career, I'm very interested in generating, synthesizing realistic human movements and how to control them to do interesting and functional movements. And computer and physics simulation is really important because we use that to realize our control algorithm, but they're always kind of just like black boxes for us. And in the recent years, I started working more in robotics. And I also realized that a lot of my robotics colleagues treat physics simulation like black boxes. But very quickly, I realized that a lot of things we need to do in control require us to really open up that black box. And sometimes we even have to innovate new black box, new physics simulation for our control. So that's sort of is a term for me in my career. I started really looking into physics simulation. Nowadays, I'm very interested in understanding and innovating physics simulation such that we can have a better prediction of the real world. All right, so today I'm going to talk about AI augmented physics simulation. Physics simulation has always been a really important, well, I would say somewhat important tools for scientists and engineers. But if you look at recent years, the prominence of physics simulation has really been elevated by deep learning, by reinforcement learning. And this all kind of started out with this desire to build AI-enabled robots that operate in dynamic and unstructured environments. Sometimes they have to interact with humans. And very quickly, we know that, just building this kind of, or operating in this complex world with a human in there is just not possible to do at a large scale in the real world. So we have to use physics simulation to do that. So physics simulation can provide a safe and inexpensive virtual playground for robots to acquire physics skills. Simulation also allows engineers to rapid prototyping different designs of the robots, easily create a wide range of the training environments, and just the sheer fact of they can quickly scale up the production of the training data is also very valuable. But there's a catch. Control policy learned entirely in simulation can fail when deployed in the real world. This is a challenge that you probably already talk about today, the sim to real gap, right? Most of the robotic researchers attempt to cross this sim to real gap by innovating better control, more robust controller. But in our lab, we're thinking, maybe we can do a lot to help crossing this sim to real gap by having a better simulation techniques. So computer animation, again, we're well known for synthesizing or simulating ultra realistic natural phenomena. But the simulation today can't really predict a particular scene in the real world, such as this particular robot manipulating this particular pot to make this particular pasta sauce, because we really don't know how to build an accurate physics model for complex interplay of multiple physical regimes in the real world at a level we know how to simulate it. Likewise, we can simulate virtual humans to perform complex motor skills that looks very cool, very compelling. But when it comes to predict the movements of this particular person in this particular environment, we just don't know. We have no clue whether our simulator is in any way reflecting the reality. So simply put, the simulation tools today is not very effective. On one hand, we have a lot of models that can create some phenomena, but they're not good for predicting any specific real world environment. On the other hand, we can collect a lot of the data from the real world, and perhaps we can build data-driven model. People been doing that a lot recently. But those data-driven models in general is really difficult to generalize to the degree that physics model and differential equations can. So what is the principal methodology to integrate data with the models we have today? So this is what I really want to be able to have. Ideally, we would love to have a customizable physics engine that only takes a small amount of the real world data from the environment, and then we can use that to use this customized physics engine to train policy that can directly cross the real world. So that would be ideal. I don't want a generic physics engine anymore. I want a physics engine that I can customize to the specific scene that I care about, but at the same time still retain generalizability. So at the heart of the simulator is this ODE, right? Ordinary differential equations. An obvious place that we can inject the influence of the data to the simulator is this parameter mu. And then you can think of a mu could be anything in your physics engine, right? It could be like the friction coefficients, could be the center of mass location, could be like pretty much all those coefficients you kind of just manually pick. And one thing we could do now, the easiest thing is that with the system ID, right? People have done that for many, many decades. We can just collect some data and then use the, try to fit the values of the mu using the data. In general, it works okay, and you should always do that anyways, but it's not a process that can scale to a high dimensional mu, right? Like in a very complex robotic system interacting with a complex world, this mu, the number of mu is huge. On the other hand, we can just throw away this OD and then replace it with a neural network and then just train that with lots of data, right? There people definitely make progress at that front as well. But as I said earlier, this is not a model that can generalize very well. So between these two extremes, we really want to be able to have a family of the methods that, on the spectrum, that can truly integrate data with a model such that they can be complementary to each other instead of overriding each other's strengths. So to this end, we need to consider other components in this physics engine, and then here I'm just talking about robotics, simulation, which is mostly this articulate rigid body system. When you're talking about deformable simulation with FEM, it's going to be a lot more complicated than what I'm going to present here. So, but still, when you're talking about robots, in the environment, the first thing you know that is that you need to be able to handle contacts and collision, right? And there could be other constraints, right? Like the boundary constraints or the bounds that you want to set for your state space and action space. For example, robots, there's certain joint limits that cannot be violated. Now our simulation framework looks much more complex, but this also means that there might be a lot more opportunities to learn from the data. So I'm going to talk about these three boxes one by one, but we probably don't have a lot of time to talk about the state and action boundary. So I'm going to focus on the first one for now today. So we start out with the conventional system ID process. Here we command the robot based on some arbitrary policy in the real world, shown as this neural network, and collect the state and action trajectory X bar and U bar. We also send the same commands to the virtual robots and simulate its motion. So now we can, the simulated motion will be compared with the real world motion in this loss function. And our goal is to find a set of model parameters, mu, to minimize, okay? To minimize the differences, of this loss function. So here I put a lock on this policy because we wanted to use this just to generate that data. We're not trying to optimize the weights of that neural network. All right, the first issue, so this is system ID really. The first issue is that with a conventional system ID, the simulation is not expressive enough to match the real world. And that's something that we often see once we are dealing with the real world data. So to make a simulator more expressive, we construct a hybrid simulator combining learnable neural networks and physics equations. We replace a manually defined constant parameters mu with a state and action dependent function. And in this way, the hybrid simulator can balance between the expressiveness that comes with the data and the generalizability that comes with the physics model. And we can then learn the parameters of the network by using the real world data. Note that we're not really we're not optimizing mu anymore. We're optimizing the parameters of the mu, which is phi. So what are the mu's? You could be very aggressive to have a lot of parameters that turn into learnable parameters. But for this particular project we're doing, we kind of still just pick a small set of mu's based on our prior knowledge or domain knowledge. So in this case, we choose the parameters in contact models such as the friction and restitution coefficients and the parameters in the actuators. Why do we do that? Because these are the two places that we don't really know the model. We don't really trust the physics model because they are known to be just a poor approximation sometimes. And also it's really difficult to measure those parameters. And then those two parameters, the contact parameters that determine the contact and the parameters that determine the actuators, turn out to kind of match the external and internal forces in the equations of a motion. So our hope is that we can probably leverage them to capture some phenomenon that's beyond the expressiveness of our physics model. So the second issue is that we don't have a good metric to measure the difference between the simulated data and the real world data. The solution is to simply learn the loss function from data, right? So we formulates a adversarial learning framework. This is the approach that you probably seen a lot, generative adversarial network, GANs. We use that to train a discriminator to differentiate whether a sequence is from the real world or it's from the simulation. And at the same time, we will train a hybrid simulator serving as a generator to generate simulated trajectories within the same distribution of real world trajectories. And the final issue here is that we will like to optimize the parameters phi directly, but we don't know how to compute the gradients through complex differentiable equations involving discrete constraints and contacts. So one option is to, we can just have a gradient-free stochastic optimization method, but those methods don't really don't scale well to high dimensional decision variables. So here the variables that we're dealing with could be it's the weights of the neural network, so it could be very high in terms of its dimensionality. So our solution is to treat the neural network part of the hybrid simulator as a deep reinforcement learning agent and use the policy gradient method to train it. Why does that help? Well, the physics equation, so first let me finish this. The physics equation together with the initial policy used for data collection, the blue neural network, now is the environment in reinforcement learning. And that part is not being optimized. With this reverse role of policy and environment, we no longer need to worry about gradients through the physics equation because the policy gradient method does not require the environment to be differentiable as long as the policy is differentiable and stochastic. So now the output of the policy, which is the simulation parameter mu, becomes the action in this reverse RL formulation, and the input becomes the state space. And the reward function is defined by the discriminator, which is being optimized and learned concurrently. So you can think about this hybrid simulator contains a policy inside that modulates the physical parameters based on the observation, based on the states and the control. All right. So once the hybrid physics engine is learned, we can use it to train robot policies. And this part just becomes very standard, right? Like you have a black box simulator now, and then you can just apply PPO, so SAC, any policy learning algorithm to train your policy. All right, here's our evaluation in simulation. We create two different simulated environments and pretend one of them is the real world and the other one is the simulated world. So in this example, we made one of the robot legs heavier, the one that's shown in red, in the real world, but the training world, the simulated world, doesn't know that. We first collect a small amount of the data from the real world using an arbitrary initial policy, like that blue policy we talked about before. And we then use our method to train the hybrid simulator. And once the hybrid simulator is identified, we train a new policy using this customized simulator in the virtual world. And finally, we test this new policy in the real world, and the new policy was able to walk with a zero shot, sim to real transfer. Here's another example. This time, the surface in the real world is made of elastic materials like a bouncy mattress. And the initial policy doesn't work because, it was just some random policy. But the failed experiences can be very useful. We collect those failed experiences and use that to train our hybrid simulator. And once we learn a customized simulator, we train a new policy and test it on the bouncy mattress. This example is particularly interesting because our physics equation, as I shown earlier, is really just articulate rigid bodies, right? But now this hybrid simulator can mimic external forces due to elastic materials without the need to simulate complex FEM models. Now, going back to our physics simulation framework, we have augmented a classic physics simulator with learnable state-dependent parameters. Next, we're going to look for learning opportunities in the state and action boundaries. The need to make this a state and action boundaries learnable becomes more apparent when we address the problem of physics robot human interaction in assisted robotics. And that's a topic that I'm very interested in. We need a better simulator for human, so that a robot trained to assist the virtual human in simulation has a better chance to be safe and effective when deployed to the real world. So this is one example. This video is a RL policy at early stage, and it's very clear, right? Like, even though you don't think garments can cause a lot of damage to humans, but the reality is, yes, it could. If you are pulling the garment in the wrong direction, in the wrong way, with a lot of force, which usually happen when you have a really bad RL policy, it can actually cause a lot of harm to humans. So training this on a virtual human is much more desired. We have added, so because of the time constraint, I'm going to kind of skip this project, but this is actually 2 projects. So our goal is to, the goal of those 2 projects is to learn a implicit function to describe or to categorize the range of human joint limits and the torque limits based on the strength of the muscles. So we don't have time to go over that. I'll just leave it as this. But I can show you a few examples of a few applications using such a human simulator. So in this project, we are interested in estimating 3D pose when the person is resting on bed under blankets. This has many healthcare applications, such as bed sore management. It's a really big problem, actually. Sleep studies, or remote patient monitoring. One thought is that we could just put the cameras in those rooms, but line of sight perception is problematic because of occlusion with the bedding. So one idea is to use pressure sensing map. In this project, we introduce a data-driven method to infer 3D poses from a pressure image recorded by pressure mattress pad. But collecting this type of training data is not easy. Alternatively, we could use simulators to give us a lot of training data, synthesize the training data. So we use our customized physics simulator to synthesize pressure images and create a large set of labeled training data. The simulation process is essentially free and allows to cover a wide distribution of the human body types. And here we show that the model trained with synthetic pressure images, but tested with real pressure images produced by real people lying on the mattress. So our model is able to predict the 3D pose and body shape reasonably well. We also use the human simulation that we built to train robot policy in this assisted dressing task. We have successfully deployed this RL train policy on the real robot PR2, dressing another robot which follows the virtual humans policy. So this robot-robot interaction scenario is an intermediate step towards serving real humans. And recently, we have also achieved assistive dressing on real users with a disability. Yeah, so here's another example of this robot policy that tries to assist a user putting her arms into the garment. Beyond dressing, we extended the simulation environment to train robots for other assistance of daily living, or activities of daily living, such as drinking, bed bathing, limb manipulation, and feeding. We developed an open source software called Assistive Gen, which is designed to provide training environments for physical human-robot interaction and robotics assistance. All right. We still have one problem. A learnable physics engine is useless if we don't know how to train those parameters efficiently, all those parameters that I talk about efficiently. We could always use some stochastic gradient free optimizer, but as I said earlier, we're not just talking about a handful of parameters now. We're talking about this anywhere in this physics simulation pipeline that needs to learn its value from the real world. So it would be great if the entire simulation cycle is differentiable. So we have the flexibility to learn any part of the physics engine efficiently. So it turned out that most of the, if we're talking about Lagrange, like the articular rigid body system, turn out that most of the physics engine is differentiable already. The only component that's not naively differentiable is the contact handling, as I alluded earlier. But this also depends on how you handle contacts, right? So here, primarily, I'm talking about if you want to solve an LCP problem to get your contact forces, then you kind of have to deal with this non-differentiability. How do we make it differentiable? So contact handling essentially is a process to find a contact force Fc and the relative velocity of the contact point in the next time step. Here I denote it as BT+1, such that they satisfy the equations that enforce contact dynamics along with the equations of motion. And this is system equation. This system of equation is called a linear complementarity program. So super short review of that. Turn out that we can write down this the next velocity Vt+1 as a linear function of a contact force with a matrix A and a vector B defined by other terms in the physics equations, and they all depend on the current state. So you have A and B at any moment. Now we can have a concise description of an LCP, which is basically a mapping from A and B to FC. Okay, and FC again is the solution of the contact force. So if we embedded LCP as a layer in the neural network, the 4 paths will be just calculating LCP or solving LCP. And our hope is that we can, our goal is to be able to compute the gradients of this layer, which is the gradients of a contact force at a solution with respect to input matrix A and vector B. Okay. And this is not, at this point, if you can consider it, just kind of solve the problem, because we have seen a lot of development, really cool math development in the last few years. So differentiating through LCP is not a problem anymore. And the way that people usually do that is to compute the gradients through its KKT condition. Well, so this is one example. If your solution, if your operator is a QP solving a QP, and you can get gradients through its KKT condition. If you look at our LCP, and it looks just like a KKT conditions for some QP, right? So if we know how to compute the gradients of a QP, we can do that with LCP as well. And that's cool. And none of this is new. It's all being discovered and formulated very nicely. So anyone who wants to solve a QP problem or embed a QP or LCP in their neural network, you could do it routinely today. The problem here is that in order to get the gradients, you need to solve a large KKT conditions, which is not ideal, because if it's in physics simulation, you want this to be really fast. We notice that this generic approach completely ignores the unique structure of our problem due to the contact physics. So if we try to exploit our knowledge in physics, we can actually develop better algorithms to compute the gradients of LCP. And this LCP is specific to the contact LCP. We know each contact points can be in one of the 3 states, right? Clamping mode, that means that contact point will remain in contact in the next time step. Separating mode, that means the contact point is going to separate in the next time step. And the tied mode, which both relative velocity and contact forces are 0. Okay, so if you know contact points are tied, LCP is actually strictly differentiable, and gradients can be analytically computed. So let's just exclude the tie case for now. Okay, we can group the contact points, the entire set of contact points, into clamping and separating, because we assume there's no tied case. And if you do that, that's what your LCP is going to look like. And it seems like we're making the problem worse, because now we have a more gradients term you need to calculate. But we know that, if the contact force, we know the contact force for separating contact point is 0, and the relative velocity for clamping contact point is also 0. These conditions allow us to cancel off many terms in our LCP calculation and reduce the LCP to the following 3 linear equations. We can then reason about each gradient term and found out that most of the terms are 0. For example, the gradient term measures how solution FC changes with the change in the submatrix ASC. Will be 0, and the reason is that you don't even need to calculate it. You can just reason with yourself, based on what you know about physics. The relevant equation for this gradient term is the 3rd one, and according to that, a value FC should map to a positive value on the y-axis. Now, if we perturb ASC, like any element in the submatrix ASC a little, we change the slope of the equation. And since the current solution AFC holds strictly in this inequality constraint, there's some non-zero room to wiggle the slope without violating the inequality. This means that the solution FC would still satisfy the inequality if we make an infinitesimally small change to ASC, and therefore the gradients will be 0. So it's really like just high school physics and math, and then you can do that for every single term and convince yourself like this is actually very little computation is needed. You really don't need to write down this entire KKT system. The only gradient terms that will be non-zero are these 2 terms in red, which needs to be computed analytically. But since they only concern a submatrix in the huge KKT system, they can be computed efficiently. Finally, we need to talk about the tide case. In fact, tide case is the reason LCP is not naively differentiable. And to see that, we can write down the linear relation of the tide contact points and plot out the 2D, plot out the relation in 2D. The current solution must lie in the origin because both velocity and contact force are 0. As we add an infinitesimally small positive value to B tilde, we see that the current solution does not hold anymore, and we need a positive velocity to balance the equation. This means that the contact will switch immediately from tide to separating mode. On the other hand, if we add an infinitesimally small negative value to B tilde, the contact in this case will immediately switch to clamping mode. And the gradient for clamping and separating cases are both valid subgradients for a tide contact points. So in theory, you could just pick any of the subgradients, and then you should still be able to converge. Your optimization should be able to converge. So in practice, encountering tide contact is quite rare due to the numerical approximation in our collision detection, right? So the takeaway here is that given a solution, the LCP contact handling is almost naively differentiable. The question is just how can you do it quickly? How can you calculate it very efficiently? So with this differentiable contact handling procedure, we now have a feature complete and very fast differentiable physics engine. Here are some results of solving optimal control problem using generic gradient-based optimizer like IPOPT. And all the examples we present here require contact states to change. And this type of a problem was difficult to solve using gradient-based optimization method before. We open source our differentiable physics engines called Nimble Physics. Anyone can just pip install and play with it. I know there's just a lot, even just today, you have seen a lot of differentiable physics engines being proposed. And that is really great. The reason we're building this is we want to start out with a physics, a feature complete physics engine that people already use that. So we start out with Dart. And we just want to make it differentiable without sacrificing or without changing or simplifying how we handle contact in Dart and without sacrificing the speed. Finally, we can make our learnable physics framework completely differentiable too, which allows every parameter in the physics engine to be efficiently learned from data. And hopefully this will open up a lot of new applications such as digital twins for robotics, biomechanics, and other engineering domains. With that, I'd like to thank the agencies that support our research. And I don't know if I have time to take questions. Thank you. I'll stop sharing.
Hi. Thank you, Professor Liu. So actually, I have a question. Yeah. So for the learnable physical simulation system, we are still using this physical simulation as the underlying model. Is that enough to simulate like real world effects? What if the real world phenomena would fall outside of those model class of physical models?
Yeah, I think that's definitely a valid hypothesis. Like, you know, you can make, even after you make every single parameters in your physics model, you know, current physics pipeline learnable, meaning itself, it's a function of the input. It might still not be expressive enough. That's definitely a possibility. I don't think we haven't hit that yet. I think our model so far is so restrictive, and for us, this is sort of a spectrum, right? We want to be able to first define a workable framework, and then we can systematically make it more and more expressive. And if one day we really, you know, get to the limit, like we know that we can find an optimal solution even with a physics engine that has a lot of different, you know, parameters, and it's still not enough, then, you know, at that point, I think you can just replace the whole thing with a neural network. My point is that we haven't got to that point yet, you know, that we need to give up our physics model yet.
I see. Thank you. Yeah. So I think we can move on to the last speaker before the panel discussion. So we have Professor Ming Lin to talk about differentiable physics for learning and control. And I'll first give a brief introduction to Professor Lin. So Ming Lin is a distinguished university professor, Barry Mirsky and Capital One endowed professor, and the former Elizabeth Stevenson Erib Chair of Computer Science at the University of Maryland at College Park, as well as John and Louis Parker Distinguished Professor Emerita of Computer Science at the University of North Carolina, Chapel Hill. She is also an Amazon scholar. She received her BS, MS, and PhD degrees in electrical engineering and computer science, respectively, from the University of California, Berkeley. She has received several honors and awards, including the NSF Young Faculty Career Award, UNC Hellman Award for Scholarly Achievements, Beverly W. Long Distinguished Term Professor, IEEE VGTC VR Technical Achievement Award, Washington Academy of Sciences Distinguished Career Award, and several Best Paper Awards. She's a fellow of ACM IEEE and Eurographics, and a member of ACM SIGGRAPH Academy. She's also a member of CRAWP Board of Directors, a former chair of IEEE Computer Society, Computer Pioneer Awards Committee, IEEE CS Fellows Committee, and IEEE CS Transactions Operations Committee, as well as the founding chair of ACM SIGGRAPH Outstanding Doctoral Dissertation Award Committee. She is an editor-in-chief emerita of IEEE Transactions on Visualization and Computer Graphics, and a former IEEE CS Board of Governors member. Okay, let's listen to the talk.
Hello? We cannot hear you.
Hello, you need to unmute.
Okay, can you hear me?
Oh yeah.
Echoes.
Okay.
You have another account logged in.
There is. Hold on a second. Can you hear me?
Yes, it's good now.
Okay. Sorry, I have two apps on, that's the problem. Okay, can everybody see my screen? I'm sharing the screen.
Yes, yes.
I could barely hear.
Yes, I can hear. I can see your screen.
Sorry for the technical problem.
We can see your screen.
Can you see my screen or you cannot?
Yes.
Okay,
Yes,
great. All right. So thank you for all the introduction. So I'm going to talk a little bit about some of the work that we have done the last three or so years, differentiable physics for learning and control. These work is our joint work with my two PhD students, Junbang Liang, Yilin Zhao, and Vladelin Koten. They are largely captures on the 4 papers that are being listed here. And I will just kind of go over some of the basic concept, which has already sort of been covered by what Karen had started already. So this is going to be easy talk following some of the contents that Karen has already talked about. So I'm going to sort of go fairly fast on some parts of these talk. And as all the prior and previous speaker has already talked about, we are really interested in embedding essentially differentiable physics simulation as a network layer in a deep neural network, so that this can enable gradient-based learning and control for all type of application, including material estimation, motion control, model-based reinforcement learning. I'm going to talk a little bit about what we did on some of these examples, given a relatively short period of time since we're running a little bit behind schedule. So I'll go relatively fast. So the basic idea here is we have trainable network layer. The differentiable physics simulation would then be treated as one of the layer that's embedded in this neural network. We will have some sort of loss function that will essentially captures the either the target motions or the target locations, or the target task that we want to achieve, or some observation. The loss function will capture the differences that will and compute the gradient to help driving down the differences or the losses toward essentially zeros or convergence, and then bring it back to the feedback loop in this sort of the deep neural network until we reach whatever task that we are hoping to achieve. There have been, in fact, differentiable programming paradigm has been really popular in the last few years. Physics simulation, it's not just one of them, but also it's taking quite a bit of interest in differentiable rendering, visions, geometric processing, and from our perspective, at least from my perspective, that I believe that there's a tremendous potential there to merge end-to-end systems that will in fact taking what we see in the real world and use that observations to help be integrated through differentiable vision, differentiable rendering, differentiable image processing, and pipe it through the deep neural network and use that to help driving the physics simulator to do things like parameter identifications, material identifications, or even use that as a way of validating the physics simulation. And the hope, at least personally, I hope that one day we can even come up with a new physics formulation or improve physics model through this kind of feedback loop. The way that we do the differentiable physics, it's very similar to what Karen has already talked about earlier. We treat collision detection, which is generally speaking a geometric problem, into essentially converting that into inequality, as you can see here. It's basically coded and programmed in the distance between the node and the face within some delta threshold, which is the delta. It's typically the thickness of a cloth in this particular example where we're looking at the cloth simulation over some delta t, which is the time step over delta t, which is some time between the 2 time step. And so this equation right here can be reformulated essentially as an inequality constraint that you see here. Then we can build an objective function which will minimize this energy of the systems using the QP formulation, as you can see, subject to these constraints, which would include things like, non-penetration encoded in the geometric formulation of the distance between 2 objects. And as already mentioned by Karen, there has been in recent year that based on the KKT condition, and you can in fact derive the implicit differentiations, which can make your physics simulation run faster. If you go through the formulation, you can in fact derive the gradients. L is the loss, it's a loss function, and you can derive the gradients for with respect to X and G and H, which were presented earlier for each one of these expression. As you could see that if you look at these expressions, they can be fairly complex and fairly large number of constraints you have to solve. And so one of the contribution that we have introduced, particularly for class simulations, is to use QR decomposition to reduce the theoretical bound of cubic down to essentially quadratic. What we have found was in practice, the theory actually reduced down to practice. We are able to improve essentially the overall computation by about 2 orders of magnitude, as you can see here. In addition, in our formulation, we also introduced the 2-way coupling between closed and rigid body. And so this will enable us to actually estimate a piece of clothes being worn by a human, which we treated as rigid body, to perform material estimation. And in this particular example, we actually compare our method against baseline and then other optimization formulations, and you can see that it not only outperforms in terms of runtime performance, but also produce the smallest errors. Another example, which I'm going to show you in just a few minutes in the quick video, is motion control, where we drop a piece of cloth, we lift it and drop it into the basket. And with our approach, again, we were able to achieve the lowest level of errors, about only 17% compared to PPO or point mass, or ours with some different formulations. And we also don't, with this particular approach, it also doesn't require as many samples because it's actually gradients. It's informing us where we need to take the sample more intelligently. And so the overall performance is speed up significantly. And this is the baseline. And this is ours with much fewer iteration. As you can see, it's only 53 iterations. It's easily, couple order of magnitude performance improvement. Also, this is the baseline with the PPO. It's about 1,000 samples, and it really is not doing such a great job. So what we have found, and this was one of our first project, is that a fully differentiable class simulation by using dynamic collision handling, where essentially we are looking at checking collision over time and looking at checking regularly, and be able to reduce using the implicit differentiation to derive the gradients, and then further accelerate the computation by using QR decomposition to essentially achieve the overall computations. So this particular exploration enabled us to have some confidence on what's possible. So we then move on to the next one, which is differentiable physics for right here, large number of rigid bodies. As the previous work that I have presented, we would like to be able to develop a differentiable physics simulation and use it as a network layer to control any kind of physical system. Sorry, I think that there was a recording here. I'm just gonna, okay, sorry about that. I actually recorded the talk earlier, and so here are sort of some of the demo that you can see. We really are looking at going beyond. We're looking at large number of interacting object, non-trivial shapes. There is actually an armadillo right there being wrapped up in the sheets. And we also have a simulated trampoline with a piece of cloth. So there is a large number of objects as well as a large variation of sizes. And then most importantly, there's actually different material types. In contrast to the prior work, mostly are particle based. With this, we actually have rigid body differentiable simulation. I was trying to delete some of the recording, apologize. So I would say that one of the biggest difference between this work is that the prior work has been focusing largely on particle-based, and then it has migrated or progressed through rigid bodies, and our own work was on cloth mesh. In this particular case, where we really are looking at what's a scalable solution. So we started looking at how do you localize your collision handling. And collision is sparse. So if you can localize your collision handling, you can do smarter clustering of collision handling, you can achieve far better performance. I'm going to skip a bit and then just go straight in light of the time. Sorry. So we are using a linear solve here. We are computing the gradient just by using the earlier formulation I mentioned, by deriving the acceleration, the loss function with respect to the acceleration to compute the gradient for DLDM and DLDF, and then. Or go here as I mean. So the key contribution for this particular work is that we are adopting the mesh as a general representation for object, and we are leveraging the structure of the contacts by grouping collisions and localized impact zone. So we found this to be particularly helpful because by not treating each one of these point contacts, but by grouping them together, you also get a little bit more stable computation as well. And we also have presented this accelerated scheme that can handle nonlinear constraint versus the earlier work was on linear inequality constraints. So this is sort of one step further in terms of overall acceleration. We have demonstrated examples, a fairly much more complex example compared to prior work. And we also have done some performance acceleration to find that approach like this. I'm going to skip some of the math here given the time constraint. But I want to kind of highlight that what we found was the approach using gradient-based approach actually outperformed the derivative-free and model-free baseline by at least one order of magnitude. And you can see right here, the formulation is actually quite similar. And I actually take one to kind of decompose and show you that, this is quite similar to what we had before in terms of a sort of computing the collision response. We're still using this vertex space formulations using the normal and the distance constraint and solving each one of the connected component as an impact zone. Okay, so I'm going to go straight to the video to kind of show you. As you can see here, there's quite a bit of difference between ours and Chen Qing. Ours is actually the red one. I'm sorry, ours is the blue one. You can see in terms of a memory consumption and the time constraint, it scaled far better using this particular approach. Let me just go straight to with our. All right, so we have also performed sort of convergence analysis, and we find that our method also converge faster than RL as well. All right, I'm going to show the video here. So some of the problem that we found that this is enabling us to solve is solving, like I mentioned already, the inverse problems, largely intensive material identifications, and also motion control. And we have embedded our simulation into the network compared to model-free RL. The star is sort of the target locations, and what we want to do is to move this object, it's a couple object, toward the star location. And you can see the converging curves as the cloth are being manipulated and moved toward the star locations. And this is the example that you have seen earlier, except now it's coming from two different views. Hopefully it highlight, illustrate the two-way coupling by using this kind of formulations. All right, I'm gonna go to the next one that will talk a little bit about articulated body dynamics. And the first two works really look at sort of cloth mesh and also rigid body interaction with cloth. We have moved a step forward in this particular work where we actually been looking at articulated body simulation as well, and extending some of the basic concept and deriving all the equations that is needed. The key messages I want to sort of take away, at least from this particular example, is we actually use the differentiable operator that we derive from differentiable physics and incorporate those into improving reinforcement learning. So our motivation really comes from the fact there has been actually quite a bit of work in differentiable physics in the recent years. And most of the recent work that we have seen have been focusing either on rigid body or deformable bodies. There are some really, really interesting and very nice work in this area. The deformable body using MPM methods, which are sort of kind of like material point based methods, they are nice, but it still doesn't handle articulation as well as it can be. So what we have proposed here, so the key idea here was we actually derive the adjoint formulation for the entire articulated body simulation workflow. By doing so, by using the adjoint formulation and derived it explicitly or analytically, we can enable 10 times acceleration over the use of auto-diff directly. We also adapt the checkpoint methods to the articulated body simulation structure. I'm going to refer you to the detail in the papers, in our paper. This particular approach helped us reduce the memory consumption by at least 2 orders of magnitude, making these extensive collections of experiences much more feasible, and also you can run it on platform that doesn't have as much memory. We also introduced 2 general schemes for accelerating reinforcement learning, which I'm going to just touch upon in a little bit more detail and demonstrate that the utility of such a rigid body simulation can be incorporated. So the overall workflow is being shown here. We assume that we have the states of articulated body, input stages, the standard state representations. Then we would update the kinematics, update the forces, just like any kind of simulation, and update the acceleration and so on. Then we have to resolve the collisions using some of the concept that I already mentioned earlier, perform time integrations. Now we have the backward and we have the forward and the backward workflow with the checkpoint scheme. So in the forward simulation, as we calculate, we store some of these state as the checkpoints going through each one of the state. And then we use these state information when we derived the backward differentiations. We found that doing this adaptively and doing it intelligently, this actually substantially reduced the checkpoint, using a checkpoint method actually substantially reduce the memory consumption. So one of the things that we have to worry about for this is to actually making sure we also have a smart structure in terms of updating our matrix formulation, the stacker matrix multiplication and calculations to combine and integrate it with checkpoint methods. There's a lot of detail. I encourage those of you who are interested to please check our papers on this. One of the things I do want to highlight was from our own experience, this is relatively early. At least we have used the differential operator or the gradients that we have to enhance the RL in two ways. One of them is we use the differential operator to improve the sampling, essentially improve the sampling efficiency. So the gradient information actually tell us, roughly around what area and what regions and what direction we needed to perform more samples. So we are able to take fewer sample and then take samples that are in the critical regions and help us improve the overall convergence. We have also come up with a new set of policy by using the gradients and an updated policy using the analytical gradients formulation. What we have found is this also improve better scalability, particularly in higher dimensional space. So if you have articulated body with high degree of freedom, this could be really helpful. All right, so again, given the time constraints, I'm just going to skip the detail, but I would encourage those of you who are interested to please look at our paper. But this is sort of where we have actually used the gradients to in fact improve our convergence, as you can see in this update here. Hopefully these two equations can quickly show you, for those of you who know about updating your samples, how we are computing this more efficiently. Okay, so very quickly, we have done some performance analysis, runtime, memory usage. We use Lecago robots, and we rendered and compared to all the state-of-the-art methods. And you can see ours in terms of both forward simulation time and the peak memory consumption. It's the lowest among all the competitor by very, very significant margin. It's at least 10 times faster than AutoDiff, and it's only 1% of the memory use for the Lecago example. We also look at the convergence and how it scales according to the number of links. And this particular approach also scale better compared to other methods. You can see ours is the blue, that's the one on the top. So the ratio of scaling is pretty much preserved. However, for the other, it's not quite the same. We also have run the sample on this Majuco end. And again, we look at a convergence analysis. As you can see, our approach using the RL here actually achieve higher maximum awards compared to the other state-of-the-art methods as listed here. So this is a revisit of the video that you have seen earlier. I'm just gonna move quickly here. So just very quick video showing a 7-link pendulum. This is really a visual comparison, as you can see, with our methods, MBPO and SAC. Ours is at least twice faster than MBPO and 4 times faster than SAC. We have also applied the differentiable physics to be integrated with gradient-based optimizations for motion control. In this particular case, we want to hit the ball into the target. And with our approach, not only we hit the target, but also faster. And this is an application of the differentiable physics to robot dropping a ball, hitting the target. And in this particular case, we actually have to adjust the friction coefficient so the car can stop exactly where we want it to stop. And with this particular formulation, not only is stop where it needs to stop exactly the way that exactly where we wanted to stop, but it also do it faster. So the conclusion here is that, you know, we have extended some of the differentiable physics formulation, derived the analytical gradients to achieve gradient-based formulation and motion control and parameter estimation, and solving other inverse problem for articulated body. We found the checkpoint methods to be very efficient in terms of reducing the memory consumption. Okay, so I'm going to sort of close off very quickly with the last example, which is we actually have taken a step further. This paper will appear in Europe this year by integrating multi-body system and soft material. And I think this may be one of the first that actually has been able to do this. The motivation here is really there has been a lot of soft robot and soft body simulations, but articulated body introduce, you know, additional challenges. So when you have these integrations of articulated robots along with soft materials, then you have all these different type of joints. The problem become fairly complex. Our motivation here was to actually solving an Amazon problem. Just a joke. I'm an Amazon scholar. That's why I'm joking. It's solving an Amazon problem, because this is really a delivery problem where you want a drone to kind of fly to wherever there's a package, and then you want to be able to pick it up. There are drones that out there that have these soft grippers that need to grip the package and then lift. So essentially you have all type of dynamics here. And our goal is to move toward that direction where you actually have articulated body with soft fingers. You can be able to grasp the object and then, you know, go to wherever you need to go. So in this particular work, we obviously build on a lot of prior work. We, you know, derive our inspiration from some of the prior examples. We adopt the friction model that was introduced on some of the prior papers. We also use the projected dynamics formulation here. We have to rederive for projected dynamics. We have to sort of rederive the implicit Euler methods formulation for the gradient computation. We have to solve this again using the optimization formulation. We have to incorporate both the local state, we have a local step energy minimization as well as a global step energy minimizations. We have to worry about how do you integrate rigid bodies along with the deformable bodies. We have to linearize our equation here for the rigid body dynamics, and obviously we also have to solve these very large system if we have large number of rigid bodies that we are treating as vertex that will be interacting with some of these soft body. So we have to find a way to reduce the dimension of the approach. We're using SVD here to help reducing the dimension approach. For articulated body, we are using the skeleton tree. And again, we have to derive the Jacobian using a chain rule, compute this recursively. So again, there are all these equations you can find in our papers. I just want to say that in our formulation, we also have to derive basically rotational joint as well as prismatic joints. And each one of them, we also have to worry about the torque and the actuations and different type of actuation as well. This was actually, as well as how actuation in muscle due to soft body. There's large number of challenges of integrating all these together. Like I mentioned, I'm not going to go into all the mathematical detail given the time constraint, but for those of you who are interested, this is really an interesting paper in terms of what needs to be done in terms of global step as well as local step update, and as well as managing the size of using some of the well-known tool like SVD to help reducing the dimensionality of the matrices that you have to deal with. We also have to deal with collision and contacts. We are, because we are dealing with soft material and also including clothes, we adopted a continuous collision detection here. And we try to group vertex-based collision handling. This is much easier to handle right now using projected dynamics. one of the things that we like to move toward and address for the future is how do you use the projected dynamics formulation on an edge-edge contact, which is much harder problem, which I don't think we have solved it satisfactory yet. So that's another sort of kind of open area for future work. We have implemented everything I mentioned here, all these different type of actuations, as well as different type of joints. And with this particular approach, we have also incorporated the checkpoint method as well, as we know that it helps reduce the memory consumptions. Okay, so we also have performed ablation study looking at our approach versus projected dynamics versus DIFSIM and MPM. And we have done all kind of comparison. We have also looked at our performance versus the state of art, and the baseline is listed there for material parameters, estimation, motion control. I'm just gonna go straight into the simulations videos so you can see the result really quick. So this is our simulations on the leftmost compared to what would look like if you don't have skeleton, and what it would look like if you only had rigid body. And this particular example looks a little bit different than prior work because we actually have a deformable clothes. And also we have deformable balls. So the ball itself actually deform as they interact with the clothes. And so the motion will actually look different, as you could see, as compared to when the ball is rigid. In this particular example, we actually have an 8-legged octopus trying to get to where the target location will be. And you could see the side-by-side comparison using our approach versus all different methods that's currently out there, where we not only simulate octopus as an articulated body, but also a soft articulated body. And again, this is another example. The fish actually have a skeleton. So this is actually a skeletal skeleton with deformable skin for the fish going toward the target. And this was our sort of motivation, where we wanted a drone to have an articulated gripper and grasp the ball and then lift. The gripper itself is also soft. Okay, so I'm going to end right here and take maybe a question quickly, and perhaps we can go ahead and move on to the discussion panel. Any question?
Can you check the? I think
there's a chat. Okay. I mean, sounds like we can. Oh wait. Okay, that was this comment's already addressed.
Hello. Yes, you can hear me now.
Yes, I can hear you.
Oh, great. Okay. Right. Do we have questions?
All right.
Okay. If not, maybe we will move to the panel stage. Actually, it looks like it's really getting harder to organize this online meetings, especially like for panel discussions. I guess we have speakers all over the world. Like there are speakers. The first speaker is Yuan Ming, and who is from China. So maybe it's not possible for him to join us, right? For those, for if you're also in the East Coast, maybe it's also like not so easy. But we have Ming, we have Lerrel, we have Yang Yin here, right? Because it's already a small group. Maybe everyone who are now in this Lerrel disappear. Oh, here. Yes, okay. You move up, turn your camera after turn the camera. Okay. Okay. Maybe everyone in room, just feel free to join the discussions. Probably, yeah, for everyone, if you like, probably you turn on your camera. That increases the engagement. Fanbo, can you turn on your camera as well? Or,
I'm working on it.
Mhm. Right. Yeah, maybe we can start from a very quick self-introduction. I guess, yeah, I'm Hao Su. I'm assistant professor from UC San Diego. I'm also the organizer of this event. And yeah, Ming just introduced herself. Yeah, we listened to her wonderful talk. And Fanbo, can you
Yeah.
introduce? Yeah.
Hi, everyone. So I am a second year PhD student advised by Hao Su. Yeah, and I'm very interested in physical simulation and embodied AI.
And Lerrel. Hey.
Hi.
Mhm.
Are you able to hear me? Hello?
Yes,
we can hear you.
All right. Hi, everyone. I'm a professor at NYU, and my research interests are in robots and how they can learn in the real world environments.
Okay. Maybe, yeah.
Are you talking about me?
Yeah.
Okay, yeah. Hello, everyone. My name is Ying, and I'm associate professor from Clemson University, and I do research in physics-based simulation, and I'm particularly interested in real-time physics.
And Yiming.
Hi, everyone. My name is Yiming, and I'm a second year PhD student at NYU. And maybe Professor Lerrel knows my advisor, Prof. Chen Fen.
Yeah.
Yeah.
Great to know you. And Wan Yue, you here?
Hello.
Yes, we can hear you. Do you
Oh,
mind?
yeah. Okay, so eventually I just joined Max Planck Institute for Informatics, and I'm currently in the preparatory phase of the PhD program. So it's really nice to hear all the interesting talks. I'm also interested in learning more about simulation technology.
Congratulations. Okay, and Hidaki, you there? Okay, good. Yes.
So introduction.
Yes, can you give a very quick self-introduction?
Sorry. Okay. So, my name is Hideki. So I belong to Waseda University in Japan as a PhD student. So, I research for embodied AI. So, namely, so vision and language navigation. So yes, I'm very interested in the platform of embodied AI, so such as AI to Soul, Habitat 2.0, and so on. Yes, it's my introduction. Thank you.
Okay, and Boyang.
Yes, can you hear me?
Yes.
Yes, in fact, I'm a first year PhD student in France, and my research interest is about closed simulation and deep learning. Thanks.
Okay, and Hector? Is Hector here? Maybe not, we will move on. Xin Chi Chin? You there? Okay, if not, maybe we'll move on. And Yuzhe?
Sorry, I'm a little bit. I just joined this meeting. I'm wondering what you are doing.
Just to give like a very quick self-introduction, and then we'll start the panel discussion. Everyone will participate.
Oh, sorry. I'm Yuzhe. I'm a second year PhD student in UCSD, advised by Professor Hao Su and Professor Xiaolong Wang. So I just joined here to listen to the spotlight.
Okay. Yeah, well, we'll start the panel discussion. Oh, Hector, yeah, your microphone is working. Please introduce yourself. No. What's that? So it's like Hector will rejoin us. Okay. Okay, probably I will start first. Okay. Actually, I understand like for who are sitting here, some of us are working more on simulation, some more on like vision and more on robotics. So probably for the questions that I will try to throw out, there will be a combination of this kind of problems. Okay, maybe let me first ask my first question, which is probably better answered by a senior member community. So I hope like Professor Ming Lin could give us certain advice. But my question is, do you agree that we are already at a breakthrough or in front of a breakthrough of simulation for robotics? Like given your long experience working in the field, what's your feeling? You feel like is it like we're somehow already at a peak, or we're gradually reaching a peak for this direction, or it's kind of like the field is just making normal progress and then we are at the average speed of the field? What's your opinion?
I don't think we are at the plateau. I mean, I think we might. I think there's still a lot of work to be done because integrating simulation along with the real world. I mean, at least my vision is I like to see that we can take real world data and incorporate it, you know, as sort of the input into this black box of any kind of learning-based algorithm, and we can get all kind of information from there to control the systems. I don't think we are there yet, and largely because the challenge of actually integrating all these dynamical systems and have them interact with each other. You know, even if you have deformable, even if you have multiple type of deformable objects, they all have different sort of stiffness, and they have to, you know, interact with each other. And I don't know if we are there yet, but I had this conversation with some people before that when people are thinking of learning-based algorithm, they are thinking like learning it's model free. And all these traditional methods, it's based on these analytical formulations. And the way I look at it is all these analytical formulations that we have derived for decades and centuries, they were all derived by essentially fitting a mathematical equation that will fit the observation. It's no different than what the machine learning is currently doing right now. And to throw away centuries of what we already have known that human has learned away, and not bringing those knowledge into this black box of neural network, it's just silly. There is no reason to do that. So that's one of the reasons I believe differentiable physics, trying to bring in these, you know, reuse some of these simulation, it's the right way to do it. This is the way I look at it, because you essentially shortcut. The better way to kind of think about this is you initialize your learning with prior knowledge. It's your, you know, you want to treat physics-based model as your prior. And if we look at that way, not only we can use this differentiable physics framework or differentiable programming framework, if we could just have them an end-to-end system, not only we do the simulation, but we also do the visions, you know, the rendering, you look at the pixel differences, you take your observed input compared to things that, you know, run through all the whole entire pipeline against your observations to see if something need to be changed, not just the parameter that could be changed, but who knows, maybe the model itself need to be changed. So that might be something that we can think about, you know, when we really get there, we can actually update the model, because we have to remember these model that we have, the physics model that we have, after all, they were the human efforts of fitting some analytical formulation to a set of observation. No different than what we are currently doing right now with learning-based algorithm, which is more statistical based. So really, it's to me, it's just all different paradigm, like converging in a way. I think there's a lot of excitement because, you know, if if there is one true law and there is one truth or one model to everything, no matter which way you get at it, they should all agree the results. And so if our neural network and our learning-based algorithm are as good as we hope them to be, that the algorithm should be able to self-correct itself as well. And so, you know, that self-correction process can self-correct itself in multiple ways. It's not just a parameter update, but who knows? Even the model that we have derived a century ago could be updated. So that's kind of like the way I'm thinking about where we are. I don't think we are there yet, but I think it will be a very exciting direction when we can really truly have these end-to-end system with differentiable framework, you know, that can bring the real world observation through the deep neural network to self-correct itself until we get the network result will match, the network prediction will match what we observed. And then even self-correct some of the model that we are trying to simulate to start with. That will be like, to me, the holy grail. And then that's when we can stop. And that's when we can, you know, stop working on this area. But right now we are not there yet. I mean, I think coupling is a hard problem. You know, that to me, at least based on what we have done, it's still a hard problem. We can't simulate the world. I mean, that's the bottom line. So far, what can we simulate? What can we embed in a neural network? You know, it's definitely not a world.
Great. Great.
Yeah, and the problem of scale is still there.
Right, that's very much connected to a second question I'm interested in. I want to listen to the opinion of the experts, actually both in simulation and robotics. So probably like Ming and Yin and Lerrel, you can each express your own opinion. So my question is, what are the bottlenecks of applying simulation in robotics research? I could come up with a number of factors, like speed, right? Can we speed fast enough? Like accuracy, right? We hear two talks today talking about how can we simulate with better robustness, especially dance talk. I feel is like the chrono engine obviously is focusing more on the accuracy side. For example, differentiability, right? We heard Karen and Ning's talk about adding differentiability. And then there'll be actually the aspect maybe we don't really cover, which is the diversity of the assets, right? Somehow we need a lot of models and many of the attributes, materials, right? Assess the simulation algorithms just cannot play their role. And then also the challenge of a software engineer, right? So somehow simulators, they are, well, simulation experts know how to use it, but for amateur users, is it very easily connected to the machine learning algorithm? Are they scalable even to like computer clusters? And then there's the teaching issue, probably even like how to train the next generation of researchers. So my question is, in your opinion, let me summarize: speed, accuracy, differentiability, assets, software engineering, and the new generation training. What do you, in your mind, is the most pressing factor that is like the bottleneck of the community of simulation for robotics research? And if we will first make a breakthrough in one of the dimensions, which you think will have the largest like a margin of a benefit? Yeah, maybe Lerrel, do you want to?
Yeah. So I think the most important thing is maybe not in your list. It's, I think, identification. Because if you want to transfer something from a simulator into the real world, even though you have a perfect way to make a simulation, how do you know what are the parameters of the real world, right? So let's say, I have a cup and, there's like a liquid inside this cup. We have a simulator for a rigid body, like a cup, and we have a simulator for a liquid, but you may need to know what's the temperature of the liquid, what's the viscosity of it, what's the friction of this cup, etc., right? So now if I have to solve a real like a task in the real world, and I have this cup and I need to figure out how to pour something, I can use a simulation only if I know what are the parameters of this. So figuring out ways in which I can identify what's the parameters of the real world, I think that's the first main bottleneck that we have at this point. I think there's a question about, do we need an exact parameter estimation or a parameter identification, or can we do it in an implicit way? I think it's an open question, not really sure. If you have a few small number of parameters, you can do it more explicitly. You can do a standard system identification on it. But if you have a lot of parameters, it gets out of hand, right? So if I have a rope or like a piece of cloth, or in Ming's talk, there was this soft body, right? So if I have a soft robot, how do I figure out all the parameters of the real soft robot? So I think that's actually the hardest problem.
Right. Yeah. I mean, that definitely is one of the harder problem, I would say. Differentiable operator can help you. The gradient can actually help you. We actually been looking at some of our work is mostly motivated by the primary estimation, which is essentially the identification problem. It's system identification problem, and that's a great point. Is the identification problem. Most of our example, like finding a coefficient of friction, that racer car, where you need to stop, what's the coefficient of the friction on the carpet. That is a perfect example. But we also have example of computing like the closed parameters, which I found out to be the hardest one. And that is, we used this material parameters model that was developed at Berkeley way back around 2011, 2012 from one of the Negrut papers. This is the paper that was developed by Huaming Wang. And when he was a postdoc working with James O'Brien at Berkeley, we used that, and it has 24 parameters. It has 24 parameters just to represent the material of the fabric. And tuning that, it's very, very difficult. We did find the gradient optimization, it's good, but it was not sufficient. So that's definitely, I think Aurora is hitting on a very, very important problem, is the system identification problem, especially when you have multiple parameters. High dimensionality is still a problem, so scalability is definitely a problem. And now I'm going to be honest though, is how sensitive are those parameters to our simulation? The real world robot is much more robust, I think, than that. But I don't work that much with real robots, so I'll defer that to Lerrel and maybe others to talk about how much that would actually really affect the robot.
Right. Okay. I think there's a very interesting aspect from what I'm hearing. So on the one side, like from the robotics perspective, right? For the simulator, if you want to stand, if you want to adjust yourself, you must learn policy as a transfer, right? On the other hand, suppose that we are sticking to the differentiability or gradient based optimization approach, right? To estimate these parameters. Say we are assuming this is the right way. And then how fast the simulator runs is a problem, right? Because if you want to do the system identification, right, speed is obviously, I mean, some bottleneck probably. So many problems are probably connected. So I think when Yang Yin works on like accelerating the optimization lot. So do you have opinions on this point?
Yeah, I think those criteria you just mentioned, those are not orthogonal to each other, honestly, in my opinion. So in many cases we talk about the performance, how many FPS we are able to achieve in the simulation. But if you don't talk about how small your residue is, and just talk about your simulation FPS is probably useless. And the cost that we need to reduce the residue or to improve the accuracy at a different level is very different. So right, so it's very hard to say whether the simulation is, or the speed of the simulation is the bottleneck, or is the scalability is the bottleneck. If, for instance, if you don't care about the accuracy that much, I would say 3%, 5% residue is acceptable. Then there are tons of very, very fast algorithm that you can use. On the other hand, if you consider something when the residue error is less than 1% or even smaller, then many the method will not effective, and you have to stick with, for instance, the standard Newton's method, and it's a quadratic convergence. So it's really not just it's coupled. Those standards are kind of coupled, in my opinion. So it's hard to say whether it's the speed or it's the scalability or something else. But at this point, I do have a question, and I would like to seek for advice from Professor Lin. And in your talk, you mentioned many times about the differentiable physics, right? And it seems to me that when we talk about differentiability, and we are pretty happy at the first order, right? As long as we are able to get the gradient or of the function of a computation procedure, and then it seems that we are happy. And do you think if we want to push forward this direction, I mean the true combination between the physics and the simulation, or the deep learning and the physics simulation, do you think we should try to harvest the power of high order differentiability? Like, for instance, we try to connect both components, not only at the gradient level, but also at the Hessian level, or maybe even further.
Right. So in many ways, we are already doing second order, right? Because most of the time our states are position and velocity. And when you differentiate, you get velocity and acceleration. So you really are, and obviously the same for the rotational component. So really we are getting, it's not first order, it's really second order. That is my perspective. Now, do we need to go beyond? It's hard to say, because I think we need to look at what our application is. And you talk a little bit about 1%, 3%, 5%. This comes back to what is it exactly sufficient? And that's the nature of the question. Like, okay, so this is kind of where theory and practice kind of, would have the tug of war, right? Because in theory, you want to use higher order, derivatives, and you want more precision. But then, and then it comes back to this issue of architecture for the neural network. Do you want a wider or deeper? And it's the same kind of question, right? And so at the end of the day, is you have to ask yourself, what's your application? And I already alluded to my comments earlier, is when we were doing all these parameter estimation, it's a standard system identification problem. A lot of people weren't using deep neural network for hundreds of years, and they get by without it. So now we do it, and it's going to take a lot of GPU compute if you do it brute forcefully. That's why a differentiable programming paradigm is a smart way to do it. There's no reason to throw away centuries of knowledge and not using that as your initial guess, or your starting point. So I think we have to ask ourselves how much compute is necessary. And it's not clear to me. That's one reason I say I think we have to ask ourselves what's a reasonable qualitative matrix, not just quantitative matrix. We can always get all the errors we want. We can always get all the numerical errors we want. No one really truly understand, at least not from my perspective, like how much of this variation in every single one of these input parameter actually is going to affect the performance of our task. We started looking into that, and that is called a robustness problem, right? So if you think about, you know, I've been collaborating with my colleagues who have been working on adversarial attack. So if you take the adversarial framework, combine it with sort of sensitivity analysis, then you start to kind of evaluate how much of an error can you really tolerate, and how much of input variation would actually induce the output performance degradation. So that's the kind of question that as engineers will probably need to kind of start thinking about. Like, you know, we're talking about 5% errors. Is that bad in our input parameter estimation? And do we really need to use a fourth order, integration methods? And so these are the kind of questions that I think we need to ask. Is we need to go back and we need to look at it. These are traditional problems, but now when you put it in the learning framework, it's very different. The good things about learning framework is if you have an end-to-end system, you can vary your input, you look at the output, and if you can establish some sort of mapping on these, this is basically input-output relationship that we will be studying is the sensitivity analysis of the system. Except now we're going to cast it in the framework learning task, right? So this might be a really interesting direction for us to kind of think about and really kind of take a step back and ask us numerically exactly what do we need? Because we don't know. I cannot tell you right now, but I do know that I don't think I need 1%. I think I can get away without that. And part of the reason is the measurement, the uncertainty in the measurement itself, generally speaking, is greater than 1%. That is just my limited observation, but people who work with the hardware can tell me more. So
Lara seems to have something to say.
Yeah. I think this is a very interesting point over here, right? Because when you have a simulation and you also so you have a thing which can do a simulation, and then you also have a controller, right? And so a controller has some inbuilt robustness in it itself, right? So if you have a controller which can sort of account for maybe 5 to 10% of an error, then you don't need your simulation to be that accurate, right? So I guess there's this sort of interplay as well between how good a simulator needs to be with how good the controller needs to be. And then another interesting aspect is that the accuracy of the controller, it depends on the task, right? So if your task is something like easy and stable, a controller can have very high ranges in which it can be a robust controller. But if it's a harder task, let's say trying to do like a balancing task or something, right? So over there, it can only account for very small amounts of this error. So I think there's an interesting interplay with how you simulate things, how you control on the robot, and what exact sort of task are you trying to solve. And that interplay can sort of inform how accurate a simulation needs to be.
So very interesting discussions. Somehow this discussion is so very much also informative to me. So what makes me feel is like we're kind of still missing an overall framework to connect the simulation with control, so that people know like their position in the whole framework and know what kind of research they could do to better bring the pieces together into the large and the real thing. Okay. Okay, so let me think about another line of question to ask. Recently, I'm seeing actually, I'm also learning a lot of ways to simulate physical, to do physical simulations, right? And then one of the questions is like the coupling of the simulation of a different kind of simulation approaches, right? So like for mesh-based or for like a MPM is kind of a volume or particle-based simulation, put them together. This is kind of a coupling problem. The coupling problem, we have listened to the talk from Ming. And maybe a nice question is like, how far away from pushing this direction? Or you think, because we're making good progress in simulating individual or embodying or developing individual simulation algorithms, and the coupling of the different algorithms is kind of a very important next topic to study. Maybe the question is not so clear. Probably it's like okay, maybe let me be very straight. There's a multi-selection problem. So one is, okay, we try to use the like a theoretical based approaches to derive how to couple different kinds of simulation approaches. And the other is probably we find a third approach that would, for example, combine many different kinds of simulation approaches. Let me give a concrete example. Like from in the past few years, there are also people considering to use neural networks to learn simulators. Yes, and then when you are using neural networks to learn simulators, it seems to ignore the coupling question because everything's just from the data. Do you agree or disagree? And is like a neural network based simulator an approach to easily connect with the downstream neural network policies? Any questions or opinions on this problem?
Okay, first of all, I agree with Ming that I hate to use pure data driven to handle physics problem. This is bullshit in my opinion. So we spend thousands of years to learn the physics, right? Human beings have spent thousands of years and the endless effort trying to understand the world we live in, and we kind of gained experience, and this lead to those beautiful and elegant systems. And now suddenly, and everything becomes useless. And as long as you have data, you can train a neural network. And this is certainly not something we should go after. This is my opinion. And regarding to your coupling problem, I think you are talking about maybe something like a multi-physics system where you have many physics phenomenon, and you want to know how those systems are interacting between each other. And
right.
The very fundamental question is that how we would like to represent the physics in computer, right? Whether we want to use a small element, whether we want to use particles, or whether we want to use a mass brain network. And those fundamental representation actually determines, or approximation determines, and the coupling or interconnection between different physics problems. And I personally, I'm not a big fan of a kind of universal simulation idea. And I'm very agree with Karen. And in Karen's talk, Karen mentioned about the customization of the simulation. So I'm really into this. So none of the numerical method, we understand that none of the numerical method is perfect and it can be applied in any condition, right? And if we want to, so for instance, just a deformed simulation, right? If you consider deformed simulation is really stiff, and then it tends to be a rigid body. However, we are not able to simply make our stiffness to infinity big to create a rigid body, because if that is the case, then the stiffness matrix of the system becomes dominant and the system becomes singular, and you cannot solve it. And then we should go back to use a rigid body formulation to model the rigid body. It's really case by case. We use different numerical model, try to leverage the properties and the phenomenon and the features of different physics phenomenon, and then try to understand what type of accuracy we are interested in, and to simulate the problem. And yeah, from I don't know how other people think, but I personally I don't like the idea, of kind of universal simulation for all, and this is really not piece of my cake.
What is the Lerrel's view?
Yeah, I think there are. I think in brought up lots of interesting points. So I think the first thing he mentioned is that trying to replace an analytical model or the sort of understanding we have from all the physics work that all these researchers have done from hundreds of years is not useful. I think we should not throw that out. But I think there are some cases in which sort of amortizing those simulations into a neural network may make sense, right? So for example, let's say you have the same environment and you're trying to do the same thing over and over again with slight variations on it. And now in a test time, instead of rerunning a simulation, if you had some like a lookup table or something of that sort to give you an answer of what happens next, you would want to use that instead of running a fully plausible or like an exact simulation of that problem, right? So I think there are like some cases in which like doing an amortization either in the form of a table, and instead of a table, you can sort of fit it into a neural network, which should give you a better interpolation property. I think there are like cases where that works well. Now, of course, it's not a general purpose solution, right? And that goes into the second point where it's, you could probably create a general purpose solution for everything, but as a practitioner, I would want to use the simulator, which is the most accurate for my task, right? And so if there's like a simulator which has been handcrafted to solve a specific task, I would want to start with that rather than trying to use one which is like average everywhere, right? So I think I totally agree at this point of view that you want to use the thing which is most accurate and most fast, right? Rather than using a single one that works everywhere. Now, of course, there are other cases in which there may not be a handcrafted simulator, and in those cases, you would want to have you may want to have a general purpose simulation there. So I think it depends on a case-to-case basis, which also I think that's exactly what Ian also mentioned. So I think I support that point of view.
So I'll just chime in a little bit along the same thought, similar thoughts, and I want to say that it's sort of kind of like, in a way, it's kind of like deja vu, having worked in computer graphics for a couple of decades now. I remember in the 80s, people were talking about particle systems, everything is all particle representation. And this is sort of kind of the very beginning of differentiable physics, where, people are looking only at particle, because this is what a graph neural network and convolution network know how to handle, right? And then as we progress, I think our group is one of the first team that really dabbling into using the mesh representation, which is much, much more commonly used in computer graphics. And yet people in neural network don't look at that. Now, obviously, we go into, we also had a paper on fluid simulation I didn't talk about. As you go to fluid simulation, then you go into grid, you go into voxel and so on. And so there is a different kind of representation. I would argue that I think it will be wise for the learning community and AI community, and those of us who are kind of across the community at this moment, to really not try to reinvent the wheel. And again, there are centuries of people who've been looking at geometric representation and what's the appropriate geometric representation for simulations. And so, using mesh, it's kind of like, hey, we know this is what works. Why would we go back to point? Just because we want to represent easily in graph neural network, right? But so I think a lot of it is just translation of language. How do we translate a traditional representation, geometric representation, physics representation and computation into sort of like the deep neural network? Now, because of that, I recently had some really interesting discussion. I'm teaching differentiable programming this semester, and I'm having like really exciting discussion with grad students who don't necessarily work with me, but other machine learning faculty. But the graph neural network, or the, you know, the GCN, if you look at like some of these representation, a lot of time we look at the graph, and whenever you think about graph, you look at connectivity of graph. And some of the problem, especially in robotics, like for example, I have to register 2 point clouds together, right? And each one of them are incomplete, but I want to register them together so I have a more complete pictures of the environment I navigate. Why do I care about connectivity again for 2 point clouds? I don't. Right. So I think these traditional, you know, thinking has to be kind of tossed away. We have to think out of the box and really look at what would be the graph representation that actually is going to be generalizable across different applications. And if that's not possible, let's at least look at the graph representation, which is going to go beyond the same graph representation that will be used for social network. And I would argue the same would be for simulation, is to come back and revisit some of these representation, because you know, blindly following whatever that was just come out may not be the way to go. And I think graph is definitely one of the very basic fundamental representation. I mean, no, you know, I mean, how has worked a lot on geometric representation of graph. So, and you know, geometry processing. So I think that a lot of those knowledge need to be somehow distilled into the new representation for the learning community and how we represent these different objects. So I think we are still there, but I want to come back and say, we do so much of adaptive methods in simulation, okay? Those are so unfriendly for a GPU cluster, as those of you who knows. Okay, that is that's my pain point. How can we get over that bottleneck? All right, I mean, that is really a pain point. Like all these adaptive methods that we have, adaptive grids, adaptive, you know, time step, adaptive whatever, doesn't work for GPU. And I think that's where the struggle will be. But anyway, I think Hector has a question, but I just kind of want to share my pain of dealing with a GPU cluster and what you can do and how it limits our creativity. I'm going to pass over to Hector, who raised his hands.
Hector? Yeah. Please ask it.
Thanks. I should start by apologizing because my mic wasn't working, so I didn't introduce myself before. So I'm a postdoc at the University of Birmingham, and I'm a computer vision person, more or less. So I kind of felt compelled to sort of play devil's advocate, I guess. I agree with many of the points, and I agree that we shouldn't throw away thousands of years of exploration and discovery about physics. But there is a counterexample to the urge to have arbitrarily accurate systems and to pick a particular system for solving a particular task, and that's us, because we don't start off with a full understanding of physics. If we did, it wouldn't have taken Newton or humanity so long to get to where Newton did. And toddlers, they learn physical concepts one by one during development. And although I'm sure you can acquire a fairly accurate internal physical model if you're an expert and you have to work on a certain task, most of us don't have models that go anywhere near the sort of accuracy that internal models that go near the sort of accuracy of the physics simulations that we develop. And yet we would probably say that for most tasks we're good enough. I mean, you wouldn't want any one person to design a Mars rover, but for most tasks, what we have in our heads works well enough. And that also goes to the issue of whether you want a specific system which is as accurate as possible for every single task, or whether you want one system or a few systems that are good enough for a variety of tasks. And that, I guess, goes to the difference, I guess, between research robotics and sort of, I guess, assistive robotics and robotics that's meant to be executed in someone's house, for example, as opposed to in a controlled environment. As researchers, we have the good fortune to be able to sort of set up our labs for the task of folding some cloth or tying a rope or building a tower of Jenga blocks. But in the real world, you have to deal with a variety of things that are happening. You have to navigate obstacles, you have to manipulate objects, you have to deal with cloth and non-rigid objects and friction and carpets and all sorts of things. And you don't necessarily get to choose which one of those you encounter at any point, because some of them come at you. So I didn't want to sort of, I'm not trying to say that what everyone's arguments are invalid, just that there is a different scenario maybe where you need to make different decisions, I think.
Okay, that's a great point. And I also agree, probably in the future, like for NeurIPS or ICML, those kind of machine learning papers, you will classify the materials and say like different kinds of simulation plus the policy, right? Each a different paper. Okay, so it actually reminds me a little bit about 10 years ago. 10 years ago, that's maybe 8 years. That was the time when computer vision started to rise quickly, but computer graphics is not as shiny as before. And then I was having a conversation with a vision researcher, and he listened to some talks by graphics researchers and said, okay, graphics researchers just making demos. Like they for a different case, they invent a different method. And then we vision researchers like the universal solutions, especially after the promising of the rise of the neural networks. But it's 2021, right? Then the situation seems to be like gradually reversing. It's like the neural networks are getting to be injected with more and more of the expertise, and those expertise are discovered through the analysis of different cases. Somehow people are getting, as you said, some of the simple problems or a large family of problems we're using generic approaches. Whereas for many of the problems that we really care about, we really need to tailor the approaches with a lot of injecting the human expertise that are from the experts that really are studying the details or are trying to build knowledge about modeling. Yeah, so it's like Yang Yin said, not everything is learned by a network, by black box. Humans know how to model. Humans know the tricks of modeling. Okay. Okay. Other questions from the audiences? Like,
sorry, if it's okay, I do have an actual question. If you wouldn't mind. So one thing I've been interested in recently is differentiable rendering and neural rendering, and this is an area that's taken off. And I mean, it's a different type of physics. It's about light transport, optics. But one of the interesting things that seems to come out of the last few years is that people have decided that meshes are actually not necessarily a good representation, particularly when you want to differentiate through things. And other representations like implicit functions can perform better because you don't have the discretization. I mean, whether it's meshes or it's particles, you have to sort of, you have discrete areas that behave individually. Does anyone have any ideas about representations that might be better than meshes, for example, for physics? Perhaps that they're not tractable at the moment. I have no idea about this myself, so this is a completely layman question. Apologies if it's a stupid one.
Maybe I can answer some aspect of your question, and then maybe other experts could complement my answer. First, the point is from a pure geometric perspective, we're talking about like a mesh versus implicit field, right? implicit functions. I'd say that the implicit function is getting more popular in terms of because of a nerve, I think. And then I would try to give one aspect to differentiate them. One aspect is okay, the generalizability. Like when you're having a neural implicit function, right? Your input is the coordinate in a 3D space, and you try to predict like a signed distance field, or try to predict like occupancy. It's kind of information. So talking about the generalizability, it's the generalizability of different spatial locations. And when people are working on the mesh networks, more times when people are talking about generalizability, it's to generalize across different shapes. So you see, one is to generalize at different input points, coordinates. The other is different shapes. And in fact, in terms of application to, I mean, you see that like implicit function is widely used like in nerve, right? This kind of application, really, you just want to get very detailed looking. So the good generalizability across spatial locations, that's important. Whereas for meshes, like in geometry processing, you like to use it for like for example, for the task of single image to 3D, people now start to use meshes. That's a kind of a shape level generalizability. And then put it in a physics simulation community. I mean, like mesh computer graphics people use it a lot, right? And there are a lot of like collision algorithms on top of mesh, right? But if you want to do collision checking using implicit field functions, I'm not as expert of the problem. It's also possible, right? It's also possible. You can also use the signed distance field and check the sign. On the other hand, what is the representation of the 3D model? The 3D model must be neural network weights, right? This is implicit.
Well, I mean, an implicit function is just a function that happens to parameterize the neural network. You could have a polynomial, you could have a wave representation. I mean, the idea is that you have some continuous surface, I suppose, as opposed to a load of discrete regions.
The question is, if you change the shape, the whole function will change,
right? Yes, although that's obviously not something that you necessarily want per se.
Yes.
I mean, you want to be able to make local changes. So you want maybe a parameter, a sort of basis functions that is local, maybe. I mean, I don't know how this would work, but was just curious whether doing this, you know, when you have triangles, you're doing collision checking, you have to treat each triangle sort of individually, and then you aggregate effects afterwards, I suppose. And I don't know whether there's another way of doing it.
There are actually papers working on like trying to learn a condition using implicit function. There's one work called MPNet, I think, motion planning network. You can check, and there somehow it's using this kind of representation to check the collision. But the issue is just the generalizability across things. When you change the geometry, mesh, you just load another mesh, which is very precise. For implicit function, it's harder. Will you load another network? Yeah. Okay. I guess we're actually already beyond the original schedule, probably. We listened to many interesting talks, and in the end, we have a lot of interesting discussions. And probably we should end up now, but we're also very welcome. If you have feedbacks to us, like have suggestions of how to organize the event better, let us know, write us an email or we can talk as well. Like we hope to have this kind of a workshop in future ICCV or ECCV as well. Okay, and thank you very much for everyone to participate.
Thank you, Hao. Thank you. Thanks everybody.
Thank you, Hao, for organizing this workshop. Yeah.
Yeah.
Bye,
Thank
everyone.
you for joining us. Yeah. Bye.
Thank you. Bye.
Thank you.